The sky above is studded with stars and countless galaxies. In them we can read not only our origin, but also our final destination. The first phase of our journey is complete. We are ready to undertake the second. With robotics, advanced technologies and sheer daring, we are now going to places that before we only dreamt we might ever reach. It was here at Peenemünde on the Baltic coast where the opening shots of the space race were fired. Not an auspicious occasion. The backdrop to this extraordinary effort was World War. The chief engineer did mutter, however, the rocket functioned perfectly, it just hit the wrong planet. Time and tide have changed that frontier. Now science and commercial imperatives lead the way. Our push into the new frontier is now genuine and humane, guided by science and the hunger for discovery. Soon it will be underpinned by the commercial realities of tourism and mining. Research and engineering advances are ongoing. New communications and sensing technologies, new space systems for advanced aerobraking, new materials and manufacturing processes for new spacecraft, and safer launch systems, all aimed squarely at a return to the moon. Then on to Mars for a long-term stay.
The human flight component would like to see an experiment where resources on the surface of Mars, from the rocks or the atmosphere, could be used to generate fuel or other parts that would enable future exploration in cutting the tie, so to speak, to Earth. So you wouldn't necessarily have to bring everything with you. You can actually manufacture it on the planet. And that's a really exciting additional component that we've been exploring and analyzing in this work.
This will extend our reach even further, with planned excursions to the asteroids and comets giving us access to even greater resources. At the same time, it would help us protect Earth from wayward objects posing a threat to our planet. Then there is the challenge of the greater solar system, visiting the outer planets and their moons. Jupiter's Europa, Callisto, Ganymede. Or Saturn's Enceladus, a potential life-harboring location. Or cloud-covered Titan, which holds vast hydrocarbon resources. Then, the great interstellar voyages to other stars and other planets. Like HD 189733b, a gas giant. Or Gliese 1214b, a water world. Or even Kepler 186f, a nearby Earth-like planet. Our first stop in this journey takes us into orbit, where we can continue to look down at the world's changing environment and study the planet we call home. We humans are mere passengers on board this vessel called Earth. We cannot control the direction she takes, how fast she spins, but we can influence her complex and dynamic ecological climate engine. To study this machine that sustains us, scientists have used satellites as one of their primary tools. Of the 6,600 satellites launched so far, some 3,600 remain in orbit, with only 1,000 still operational.
There are two main sorts of satellites that we use for weather forecasting. The first sort is the geostationary satellite. Now, these geostationary satellites are launched into orbit at 36,000 kilometers above the Earth's surface. And at this height, they orbit the Earth precisely once per day. I can illustrate it like this. The Earth rotates around its axis on a 24-hour basis, and at the same time, the satellite orbits the Earth. So it always stays over the same point of the Earth. In this way, it takes an image of the Earth, now with our MSG series, every 15 minutes, and it can provide very high rapid update cycles from that data. The other main sort of weather satellites we have are the polar orbiters. Now, these orbit the Earth at a much lower altitude, about 800 kilometers, and they orbit pretty much over the North and South Pole in what we call a sun-synchronous orbit. Now, because they're much lower down, they're able to provide us with a much more detailed view of the Earth and the atmosphere.
The complexity of the Earth climate model is due to a range of variable inputs, from solar radiation, solar winds, magnetic fields, gravity, thermal absorption, to water temperature and salinity, ice and cloud coverage, carbon dioxide and other trace gases in the atmosphere, to name just a few. The first order of business has been to monitor our weather. Maximum scientific value comes from long-term data gathering. It has to be reliable, continuous and uninterrupted. To this end, ESA and EUMETSAT have launched their latest satellite, METOP-B.
METOP-B is particularly important to provide continuity of this data. This data has the largest single impact into the weather forecasting system. So it's very important that we maintain this capability, and for climate purposes it's very important that we maintain a continuous record in time.
Apart from accurate weather data, it also carries a GOME, or Global Ozone Monitoring Experiment. It monitors ozone concentrations in the polar regions.
This is an instrument that measures in the ultraviolet and visible part of the spectrum to retrieve information on the ozone structure in the atmosphere, which is particularly important for understanding the recovery of the ozone hole, and also it's now used within weather forecasting itself.
Weather forecasting is important for everybody because weather impacts a large amount of society, economic aspects. It impacts everyday's life. Satellites improve weather forecasting, so improved forecasting enables us to provide earlier warnings, better warnings, give us more time to warn.
There is now a concerted and coordinated effort by the major space agencies, NASA, ESA and JAXA, along with their international partners, to launch a series of next-generation Earth observation satellites, each with specific instrumentation to address the many variables making up our climate. Joint partners NASA and the Japanese Space Agency have launched an international satellite mission, GPM. The Global Precipitation Measurement Mission will set a new standard of observation of rain and snow worldwide. GPM consists of a core satellite with 8 constellation satellites. With precipitation radar and a microwave radiometer, the system will collect global data every 3 hours.
The GMI produces a critical reference standard which unifies all the member satellites of the GPM constellation. The instrument has 13 channels, and this greater sensitivity allows GPM to measure a greater variety of precipitation type and intensity. Each channel has a frequency range that can detect a different type of precipitation. Scientific algorithms then translate the GMI's brightness temperature data into more meaningful products, such as rain rates. Because GPM's coverage extends beyond the tropics, measuring storms like these in the mid and high latitudes will improve and expand the global view of precipitation.
Conducted with the National Oceanic and Atmospheric Agency and the space agencies of France, India and China, the GPM mission data will advance our understanding of the water and energy cycles and extend the use of precipitation data to directly benefit society. Two major components of Earth's climate system are the water cycle and ocean circulation. The joint US-Argentinian Aquarius Satélite de Aplicaciones Científicas mission can map the salinity or the concentration of dissolved salt at the ocean's surface. By measuring ocean salinity from space, Aquarius will provide new insights into how the massive natural exchange of fresh water between the ocean, atmosphere and sea ice influences ocean circulation, weather and climate. One of the oldest and most venerable satellite missions to date is Landsat. A NASA and US Geological Society project begun in 1972 with the launch of the first Landsat satellite, it is the longest-running contiguous Earth imaging program. The 8th of the series is currently in orbit.
It orbits over the North and South poles, taking imagery on the sunlit side of the Earth every time it passes.
The Landsat 8 satellite makes 14 orbits per day and covers the entire globe every 16 days.
The data from the Landsat data continuity mission will be the best data that have ever been collected from a Landsat satellite. With increasing population, our land use are changing at rates unprecedented in human history. To manage and cope with these changes, we need to have the observations, the information, the data that allow us to understand what's going on the surface of the Earth where most of us live.
The data collected over 40 years of the Earth's surface has created an historic archive unmatched in quality, detail and coverage.
Landsat archive that contains all of the US-held data from all of the Landsat satellites, and the LDCM data will become part of that archive.
The Landsat program offers, free to anyone, the longest global record of the Earth's surface, and it will continue to deliver visually stunning and scientifically valuable images of our planet. However, the Earth's surface is predominantly water. Measuring the topography of the oceans is another challenge altogether. Begun by the Topex Poseidon satellite, a joint effort of NASA and France's Centre National d'Études Spatiales, and continued by the Jason-1 satellite, their latest mission is Jason-2, continuing to provide a long-term survey of Earth's oceans. It measures changes in the height of the sea's surface. These are used to understand shifts in ocean currents as well as sea level rise, both critical parts of global climate change. The data is used around the world to improve weather, climate and ocean forecasts. Another ocean-going measurement is the speed and direction of the winds. The Sea Winds Scatterometer is a specialized microwave radar that measures near-surface wind. The scatterometer estimates wind speed and direction over the Earth's oceans at 10 meters above the surface of the water. The instrument collects data over ocean, land and ice in a continuous 1,800-kilometer wide band, making approximately 400,000 measurements and covering 90% of Earth's surface in one day. Earlier satellites could only image the uppermost layers of clouds. CloudSat was among the first satellites to study clouds on a global basis. It looked at their structure, composition and effects. The key observations are the vertical profiles of cloud liquid water and ice water contents and related cloud physical and radiative properties. CloudSat flies in tight formation with the Calypso satellite, carrying a backscattering LIDAR, and these two satellites follow behind the Aqua satellite in a somewhat looser formation.
When we started with AIRS on Aqua, we had two goals defined to us, before the mission started. One, provide data to the nation's weather forecasting center, which is NOAA, and improve weather forecasting. So that was the first goal achieved, and we, the science team, felt good. The second goal was improve our understanding of the climate system, the water vapor. That is the main mechanism by which weather and climate is formed here on Earth.
The combination of data from the three satellites provides a rich source of information that can be used to assess the role of clouds in both weather and climate. The European Space Agency's Earth Explorer program has seen several high-tech satellites play their part in our understanding of the global climate.
We have launched 3 missions, meanwhile, with fantastic results and very innovative technology.
SMOS, the Soil Moisture and Salinity satellite, observed soil moisture over the land and salinity in the oceans. Cryosat, the ice mission, measured the thickness of the massive ice sheets over Greenland and Antarctica and the marine ice in the Arctic. It used a sophisticated stereo radar system and has helped give us a better understanding of the relationship between ice and global warming. GOCE measured Earth's gravity field with unprecedented accuracy. A geoid model is crucial for deriving accurate measurements of ocean circulation and sea level change, both of which are affected by climate change. This data revealed the Earth to be lumpy and quite variable across the planet. It has led to a new map of the boundary between the Earth's crust and mantle. Another piece in the climate puzzle, and a critical one, is the Earth's magnetic field.
The Earth magnetic field is our lifesaver, there's no doubt about this. This shield is basically protecting us from the harmful effect of the solar wind, these high energy particles that the sun is constantly bombarding us with, and this shield is really essential for us and for our protection. The main magnetic field of the Earth is changing in time, and it is weakening by a factor of, let's say, 10–15% or so over the last 200 years. And what's actually going on in the outer core of the planet is what we really try to find out. The magnetometer package on board Swarm, it measures the magnitude and also the direction of the Earth magnetic field. And it does so in 2 locations. One, it has an instrument at the tip of the boom and also another instrument halfway down the boom. And together they give all this precise information that we needed to decipher the secrets of the Earth magnetic field.
ESA is now developing a new family of missions called Sentinels as part of their Copernicus program.
It is not sufficient to monitor the evolution of the ice cap or to monitor the sea level rise during 5 years and then stop. We really need to monitor those things over a very long time period. And this is what Copernicus will bring. It will bring a long-term frame for continuous monitoring of our environment.
Sentinel-1A is the first of a 2-satellite mission that will scan land and oceans using advanced radar to deliver imagery regardless of weather.
Copernicus is the most ambitious Earth observation program to date. The European Space Agency is putting together 6 families of Sentinels that will take care of the objectives of the Copernicus program, monitoring the land, the marine environment, the atmosphere, climate change, and providing a fast response to security and emergencies.
In total, there will be 6 Sentinel missions, each pair of satellites devoted to specific observations.
each Sentinel has a specific duty. Sentinel-1 is more specifically tailored to emergency response. Sentinel-2 is focused on monitoring of the land. Sentinel-3, together with Sentinel-6, is focused on the monitoring of the ocean and waters. Sentinel-4, together with Sentinel-5, is specially tailored to the monitoring of the atmosphere.
The International Space Station is also host to several climate sensors. Currently, the CATS, or Cloud Aerosol Transport System, is mounted on the Japanese Experiment module. Using light detection and a ranging LIDAR system, it detects and measures pollution, dust, smoke and other aerosols in the atmosphere. NASA will be installing another instrument, the RapidScat, onto the end of the station's Columbus module this year. It will measure ocean surface wind speed and direction and help improve forecasting and hurricane warnings. The Orbiting Carbon Observatory was NASA's first satellite dedicated to the tracking of carbon in the atmosphere, how it is reabsorbed into the biomass, and where. Unfortunately, a launch failure has caused a reschedule of the project.
But we need the measurements that spacecraft like OCL will make in order to understand the processes controlling the rate of buildup of carbon dioxide in our atmosphere so that we can understand how it will change in the future.
Other projects in motion include the Atmospheric Dynamics mission Aeolus with its high-power UV laser, which will measure wind speed, air moisture and dust particles to advance our understanding of atmospheric dynamics. EarthCare will study how the Earth reflects and traps heat. Biomass will study the state of the Earth's forests. NASA's Clario satellite will measure incident solar irradiance and the Earth energy budget. SMAP, the Soil Moisture Active Passive, is an Earth satellite mission designed to measure and map Earth's soil moisture and freeze-thaw state to better understand terrestrial water, carbon and energy cycles. The suite of satellites now in orbit and planned for the near future will be able to peer beneath the clouds, vegetation and other surface features, monitor water salinity, temperature and energy fluxes, chart ocean currents and the change in ice caps. All this data is helping to improve our understanding of climate change and also helping in a practical sense, with flood and drought monitoring, hurricane and cyclone warnings, understanding changes in water availability, food production, and the other societal impacts of climate change. "100 kilometers above the Earth's surface lies an invisible frontier, the edge of space. This is the Kármán line, the boundary between our planet's atmosphere and what lies beyond. What does it take to cross that line? To date, some 450 cosmonauts, astronauts, taikonauts, the names all mean the same, have crossed that unseen line. Cold War test pilots to begin with, then geologists, engineers and scientists of one kind or another. Mission specialists now come in all sizes and nationalities. Even politicians and cashed-up tourists have gate-crashed the space party. But how do you earn an astronaut's wings? As Chris Hadfield, the first Canadian to walk in space, has said, an astronaut's life is one of preparation and simulation, and training and support on the ground, and anticipation and visualization. And very, very seldom, almost never, is an astronaut's life about flying in space. In one sense, the key to becoming an astronaut is simple: brute force. But selection for space is an exhaustive process. Astronaut candidates must be fit, physically and mentally, to endure the rigors of training. High intelligence is essential, while bravery is a useful character trait. The current crew of astronauts have trained for work on the International Space Station, while others are working towards missions yet to come. They have one thing in common: they all consider themselves lucky.
I never planned to become an astronaut. I mean, I knew that it's a very small likelihood, and so as a scientist, I knew the statistics, meaning like, okay, if I try to become an astronaut, it probably won't work out. So for me, applying with ESA to become an astronaut was not as much a thing of me believing that I would become an astronaut, but more trying to give my dream a chance that I had, that I knew I was always looking forward or trying to see, do I have a chance to actually go there?
It also helps if you know how to use one of these.
I find my background as a pilot very helpful, just in the way that I've previously been taught how to follow procedures, for example, as a pilot, communication methods, working together in a team in an international environment. All of those sort of skills are very useful in this job.
Of course, I had expectations before I started. But the job as an astronaut is so unique. I think it's difficult to have a realistic sense of what to expect. So certainly some things have been what I expected. I mean, the excitement, the uniqueness, the wonder of human spaceflight is exactly what I thought it'd be. Other things, of course, have been different simply because it's such a unique world to train for a mission.
Astronaut candidates should expect a 2-year period of training and evaluation. Learning to live and work in extreme environments comes right at the start. Movie buffs will recall Key Largo in Florida as an isolated place for Humphrey Bogart. Now it houses NASA's NEMO facility Aquarius, training astronauts for both the ISS and future asteroid missions. Other unwelcoming environments used for isolation and team building include the Sagruta Caves in Sardinia, Italy.
The ESA Caves mission that I was a part of a few years ago, where I spent a week living underneath the ground in a gigantic cave system, the 2 NASA NEMO missions that I've been able to participate in. I mean, all these things are fantastic opportunities in and of themselves. And just having those opportunities without going to space would be fantastic. But so to have them and then to go to space as well is just really it's what makes this job so unique and so fantastic.
Of course, spaceflight training is not easy. I think that's clear. I mean, for 3.5 years, you have to travel almost every 3 weeks. You fly over the Atlantic, you're in different training locations. You spend about 5% of your time at home. And if so, maybe then just a weekend here or there. So it's a challenge.
Training takes us all around the world into every center. I've already done 2 or 3 orbits around the world, but just in a plane going from NASA to Russia to Japan and back to Europe. So it's already, the training as an astronaut in itself is already rewarding. I mean, it's already the dream job. And even better, it gets you to a flight in the end. So there's no time to be bored. There's no time to think too much about what you're doing. Every day you're busy, every day is a good day, and that's going to continue until the flight.
Use the ladder. Okay. Careful, and I'll just follow you. And we'll sit down there.
Space training in Europe begins at the European Astronaut Center in Cologne, Germany, where trainees learn the essentials of maintenance and repair of onboard systems.
You would be asked to actually either remove or clean or just inspect the filter. We would need to close the ladder.
They also continue their basic EVA training in another unfriendly environment, underwater.
In general, the training at the different locations varies quite a bit. First, there's the technical side, which means like we're training in Japan on the systems that Japan supplied to the space station. In Russia, we're training on the Russian segment of the International Space Station. In the US, we train for the US side. And at ESA, we train for Columbus and ATV, which are the modules that ESA supplied to the space station.
Next, the candidates move on to NASA's larger Johnson Space Flight Center in Houston, Texas, for extensive EVA training.
Training at the JSC is always very busy because we do many different things and it's a huge facility, so we're moving all the time from one building to the other. Like here we are in the building 9 where we have a replica of all the American modules of the space station. So in this building we train for the space station. Some of it is daily operations, some of it is actually off-nominal operations like emergencies. Like in these mock-ups in this building, just yesterday I did a 5-hour emergency simulation with my crewmates, with our full crew complement of 6 people of Expedition 42. And that of course is not something that you would call daily operations. That's something that we really don't want to happen, but we train it a lot because emergencies would put us as crew in danger.
Here we go.
HCN 1.2.
The great thing about being trained on emergencies is that it gives you a state of mind. Having the knowledge, having the training can help you in any situation, in any condition, just like it happened to me during my EVA. It was an unexpected emergency that we had not been trained for, but because you have received training that it's all encompassing, it gives you the state of mind where you look forward to the solution rather than focusing on the problem.
EVAs, extravehicular activities, sound routine enough. But spacewalks, as we know them, are among the most dangerous duties an astronaut must carry out. Preparation and safety-conscious planning are critical.
Behind me you see a lot of equipment which is related to the airlock operations in case of a spacewalk, so we train this here as well. But there's also another completely different facility, which is the Neutral Buoyancy Lab. That's a huge pool, and in there we train for spacewalks underwater.
Neutral buoyancy training tanks are in place at ESA's Cologne facility and at Star City in Moscow, but JSC has the biggest.
EVA training is fantastic. It's physically difficult. It's one of the most challenging parts of the training, but it's also one of the most realistic. When you're in the pool for 6 hours, you get tired, but at some point you really think you're on the ISS. You look around you, and there's a structure everywhere. Sometimes you even get disoriented because that's what happens in space. It's like a 3D labyrinth of technology. It's a maze of technology.
There is so much going on here because we not only train space station, but robotics, spacewalks. So it's a very complex training system, and it's very exciting to be part of it.
I think one of the hardest parts of the astronaut's job is to retain all this different information over the 2.5-year period from being assigned to actually launching. Yeah, there's an awful lot of information on the Soyuz, on the space station itself, robotic training, EVA training, the list goes on. So to try and retain all that, the way that they do that is just by having refresher training really along our path to launch.
JAXA, Japan's space agency, trains astronauts in the operation of the country's ISS contribution, the Kibo Experiment Module, with its space exposure platform.
I guess it has a very Japanese flavor to it. I mean, the content and the way the content is presenting and delivered is pretty much standardized. But of course, you know, the instructors are Japanese. They have that very polite, very kind Japanese way about them.
In Saint-Hubert, Quebec, the Canadian Space Agency's Mobile Servicing System Operations Complex schools astronauts in using robotic arms on station.
Here's a station at scale, and here's a robotic arm also at scale. It moves and we can plan our maneuvers. As you can see, the main challenge to not hit anything while you're moving this arm, because all you got really when you're working, if you come here, there's this workstation. You got a couple of camera views to work from. You got your hand controllers to move the arm, and you get some computer displays and a bunch of switches here on the left. That's all you got, so you really got to think ahead how you're going to maneuver this arm without crashing into anything, because of course that would be a very bad day on orbit.
Star City near Moscow in Russia was the birthplace of manned spaceflight. It remains a key training center, where all ISS-assigned trainee astronauts go through the program.
When you first start in Star City, you immediately feel like you're part of something bigger than just your own personal history, because your personal story, because you see people who've been here since the beginning. There's even supposedly Yuri Gagarin, his wife, is still living here, even though she's very old, she's still living in the vicinity. So you just cross people in the corridor, and they've known all those guys, and I was just a kid, and those guys were already in human spaceflight. So you try to learn as much as you can, you try to do your best for the technical side of the job, and try to interact as much as possible with the people, because they're so experienced that they have a lot to give you.
Expecting the unexpected is a basic training principle, like landing off course after the mission or touching down in the Siberian tundra. As NASA has no manned flight hardware of its own at present, the agency purchases seats on Russia's Soyuz spacecraft. All astronauts must be trained on the Soyuz systems, which poses a problem of its own. Everything is, of course, in Russian.
All the documentation's in Russian in the Soyuz spacecraft, and of course all the conversations in Russian as well, which is the reason for us having all of the Russian lessons during our training flow.
Not only must you know the Russian language, when in Russian spacecraft, you must also wear Russian spacesuits.
When the Sokol spacesuit actually pressurizes, things do become much more difficult to work, because you're kind of fixed in your seat in a very rigid location, and it's hard to bend your arms and bend your fingers in fact. So even just sort of reading the board documentation can be quite difficult. But hopefully you won't be pressurized when you do a normal descent. Hopefully the spacecraft will come down without any problems, and your spacesuit will be much softer which makes it easier to move.
Here in Star City, I'm using most of my time in the Soyuz simulator together with my commander. Suddenly it's starting to feel a lot more real, you know, when you're sitting in the Soyuz and you're really going through the whole launch and landing sequence. You can feel that you're getting close to the date, and it's very, very exciting.
It's a very well-oiled machine, this flow to launch, and I'm confident that, you know, by the time every astronaut flies, you're really ready to go. You're prepared in every way.
As things stand, an astronaut bound for a 6-month mission to the ISS needs up to 5 years training, a requirement which will, in all likelihood, be intensified for future missions to deep space. The ISS will probably be used as a long-duration astronaut training facility for missions to Mars and beyond.
We are also all people that are selected to be able to get along with each other. That's kind of like the way you select astronauts nowadays for long-duration space flights. You really want to have people that are balanced, that are easy to get along with other people.
So much of our work up there is determined by the visiting vehicle traffic, and that's a very dynamic phase because we're not quite sure exactly which vehicles are going to arrive when.
I got 18 centimeters.
And these vehicles bring up a lot of science, they bring up a lot of hardware that determines when the EVAs are done, and also they of course determine the robotics activity that goes on to capture the vehicles. So when you're not quite sure what the visiting vehicle schedule is like, you're not quite sure exactly what science and when it's going to be done on board the space station.
One 6 months increment for the whole crew is around 300 experiments, out of which there's 55, 60 for ESA. So there's a wide array of domains like medicine, technology, material science, fluid science, everything you can think of. We're trying to make the most of the conditions in space and the microgravity to get results that wouldn't be possible to achieve on Earth.
So one of the things I've learned is you just have to be extremely flexible, and we get trained on how to do tasks that may be planned 6 months ahead of our mission and maybe planned 6 months after our mission, so that should there be some flex and those activities fall within our increment, then we're trained and we're ready to do those as well.
There's some leftover smell.
Whoa. Is that good?
Not good.
Looking out of the window is really one of the most fantastic experiences that you can have from the International Space Station. Our Earth is so beautiful, and yet when you look outside you see that the atmosphere that surrounds our Earth is so thin. It's merely like an eggshell around an egg. It's so fragile, and the vulnerability, the fragility of our planet is very, very visible from on Earth. You see this blue ball, and then above nothing, just black, absolutely nothing in this immense universe. And I would hope that more people would be able to fly to space, more maybe of our politicians, decision makers would be able to fly to space and really see the vulnerability of our planet, so that we can finally start doing something about climate change.
Been used. So the way it installs, this needs to be in the flush, but we can come over here so you can see. Dual lock to get to the more cut.
We're just so prepared. All the emergencies, all the possible failures, we train them over and over and over again. So we're supposed to be able to handle any situation. We sat in the simulator hundreds of hours. We know the systems inside out. So there's nothing really that we fear, I think, on the technical side.
Even with all that training, astronauts are well aware of the dangers of spaceflight. Riding a rocket full of explosive fuel, living in an enclosed environment with a thin sheet of aluminium between you and hard vacuum, solar and cosmic radiation, bullet-like micrometeorites and space debris. Then there is the threat of onboard fire or mechanical failure, and to cap it all off, the fiery return to Earth. There is, however, one problem that returning astronauts cannot avoid, and that's gravity.
When you get back home, of course, I will always remember this was the same for my first flight or for my second flight. The moment they open up the hatch and you feel this fresh, cold air coming into your capsule. This is really something. And you're out there, of course, in the steppe. You have this real soil kind of smell that you have. It's really feeling fantastic. And then they get you out of the capsule. And the first thing, of course, that you want to do is to contact your family, your friends, saying, I'm all right, everything is great. We will see each other tonight. And then you just want to rest and to sleep because you're so tired, of course, from this long day of coming back. And also the gravity is really then having an impact on your body. You can't, it's difficult to stand up. It's everything that you have to lift. It's hard, it's difficult. And this takes a couple of days. But after a couple of days, of course, you recover well. We have a very good recovery program here at our European Astronaut Center. Our people are really very focused on getting the astronaut back up to the level as he was before the flight as soon as possible. And then, of course, it's again, after a while, business as usual.
I'm reaching the end of my career and I'm being able to do a last flight and really, again, put at work for myself, but also for everybody else, all the knowledge and know-how that I've acquired during this year. It's a very great opportunity, and I'm really happy that I've been assigned for this.
There is another way of crossing that unseen line on the edge of space, by paying your own way as the ultimate tourist. A number of wealthy individuals have already done so. Soon enough, it will become cheaper and accessible to the ordinary mortal, provided he or she can pass the medical.
You know, when our test pilots and wonderful team that run Virgin Galactic say that we're ready to go, then I'll be ready to climb in and be the first passenger as such, to go to space and to become an astronaut, and from there, hopefully, thousands of people will follow me.
The Moon, our closest celestial companion, our indispensable dance partner through the cosmos, lighting our night sky and gently tugging at our shores. Few have walked on her surface, but her allure remains strong. Once again, we are glancing her way with renewed interest, and with a view to returning very soon.
Houston, Tranquility Base here. The Eagle has landed. Roger.
When I was a little girl and people were always asking me, what do you want to be when you grow up? And I used to always go, I want to work up there. As an engineer, you dream of a job like this where you get to follow in the footsteps of some of your childhood heroes. And of course, for me, the Apollo missions, seeing these folks on TV step on the moon and work for NASA, as an engineer, it's just a dream to be able to say, I want to do that too, and here I am.
Only a dozen Americans have kicked the dirt on the lunar surface. It was a bold and dangerous engineering achievement driven by a political agenda.
The Apollo program was important
because it showed that we could leave our home planet and visit an object like the moon. However, what we want to do next is learn how to live and work off of our home planet on another planetary surface, like the moon. By developing this capability, we'll be able to know how to go throughout the inner solar system, which has many important destinations, both for science understanding and also may have economic importance for not only our generation, but for future generations.
The Soviet Union and the US had peppered the lunar surface with soft and hard landing spacecraft. The Soviets' Luna 24 was the last of that program, returning soil samples that contained traces of water. Much of science and technology has advanced since the 1970s. The mechanism of world politics has evolved, new partnerships have formed, new players are looking skyward, and more recently, private enterprise has taken up the challenge. With the faintest of inklings that there may be usable water on the moon, a forensic focus has turned to the southern polar region. Scientific programs in the 90s refocused on the moon. Japan was the first to revive lunar research, and only the third nation to achieve lunar orbit with Haiten on a dust-collecting mission. The US followed with Clementine, a joint NASA military project. It completed a mapping survey of the lunar surface, along with gravitational data and evidential proof of possible water ice hidden in a south polar crater in permanent darkness. 4 years later, Lunar Prospector mapped lunar resources, gravity and magnetic fields. It was also impacted into the southern region of the surface to elicit more evidence of water ice hidden in the craters. Europe's contribution to this resurgence in lunar exploration began with the launch of SMART 1. This tiny, ion-propelled satellite catalogued key chemical elements on the surface. It also enhanced the theory that the moon was the result of a collision between Earth and a smaller celestial body called Theas some 4.5 billion years ago. Japan's second probe was Selene, better known in Japan as Kaguya. It continued extensive observations of the lunar crust and also carried the first high-definition cameras into lunar orbit, giving us a clearer picture of the rugged surface. Another proof of capability, this time by India. It also carried a NASA mineralogy mapper and an impact probe. It played a key role in the confirmation of water hidden in the southern lunar pole. 8 months later, NASA launched the Lunar Reconnaissance Orbiter, or LRO. It has spent the last few years mapping and scanning the lunar world with sophisticated sensors and continues to return a wealth of data.
The Lunar Reconnaissance Orbiter is, as its namesake says, a reconnaissance mission to the moon. Our job is to take a suite of very powerful scientific instruments and make an atlas of the entire moon, in some places in very great detail. Topography, mountain heights, mineralogy, temperatures, abundances of resources, including potentially the intriguing possibility that there's water at the moon. We put all this together into a data set by flying low over the moon for a year. This is the data that the people designing the human systems, designing the systems, picking the sites, need to take us back to the moon.
This robotic mission commenced operations in June 2009. It was hoped the suite of sensors would fulfill several scientific goals, not only for the moon, but as a framework for understanding planetary processes throughout the solar system.
The LRO instrument suite is comprised of 6 instruments and 1 technology demonstrator. And they are geared towards providing us a variety of data sets ranging from a thermal map of the moon, global topography, and most importantly, looking for resources like water ice on the moon. The entire suite should provide more of an atlas as opposed to a map, so that we know where to go on the moon, where to have the safe landing sites, and where to put things like lunar outposts in the hopes of having human exploration in the near future.
The data being returned from LRO and the other probes draws a clear image of the evolution of the lunar surface and why it is composed of exactly the same elements as the Earth. After coalescing from the Earth-Theas collision, the proto-moon cooled, then suffered several major collisions from orbital debris, which created many of the largest surface characteristics, including the mares. Cratering continued relentlessly over the millennia, drawing the familiar lunar vista.
My name is Lynn Carter. I'm a research space scientist, and I work with the Planetary Geodynamics group here at Goddard. I study the geology of planetary surfaces, the Earth, Moon, Mars, Venus. There's a lot of things you can learn about the Earth by studying other planets. For example, on the Earth, we have a lot of erosive processes. You know, it rains, it washes parts of the surface away. We have plate tectonics, which recycles the crust. But on other planets, those processes don't necessarily occur. So for example, when we look at the Moon, we're seeing a surface that's much older. We can use impact cratering on the Moon to sort of understand how many impacts happened, the size of the objects that were hitting each other in the early solar system. One of my favorite things is to use radar remote sensing. For example, on Mars, we can use radars to sound all the way to the bottom of Mars polar caps and see all this layering within the polar caps. And on the Moon, we're using it to study impact cratering. Sometimes when an impact crater is formed, a huge sheet of melt is thrown out. This melted rock flows across the surface, but then over time, it's covered over by stuff from other impacts. But with the radar, it just blows right through all of that, and you can see this beautiful image of the melt flow coming out of the crater.
Launched with LRO was LCROSS, or Lunar Crater Observation and Sensing Satellite. It deployed sometime later than LRO and had a finite mission. LCROSS and the rocket stage that delivered it were deliberately crashed into the craters of the South Pole, whilst LRO orbited above and observed the impacts. The debris and gases thrown up from the lunar surface were closely studied by LCROSS as it too descended to the surface. The missions found evidence that the lunar soil within these shadowy craters is rich in useful materials. The Moon is chemically active and has a water cycle. Scientists also confirmed the water was in the form of mostly pure ice crystals, which had not seen sunlight for billions of years. LRO has continued to operate in polar orbit, making observations of the South Pole, and with repeated flyovers, it has drawn up a detailed map of neutron densities in the region, revealing where hydrogen and thus water can be found within the lunar soil. The importance of this discovery cannot be overestimated. Having this resource in situ means independence from the cost and effort of bringing water from Earth to the Moon. It can be used for creating rocket fuel, oxygen to breathe, water to consume and to irrigate crops, and used in other processes to manufacture building materials from the lunar soil. Launched in 2007, NASA's 5 Themis spacecraft have now successfully completed their 2-year mission to determine the cause of geomagnetic substorms. Because they are continuing to work perfectly, NASA redirected the outermost 2 spacecraft to the Moon. This new mission was called Artemis, and they studied the magnetospheric environment near the Moon. They also observed the effects of surface electric fields and ions from the solar winds on the lunar surface, and determined the internal structure of the Moon from variations in its magnetic field.
Well, in a nutshell, what we're finding is that the polar craters are very unusual electrical environments. Well, the solar wind is actually a relatively tenuous gas that's emitted from the sun, but it's not a neutral gas like the gas in this room. It's actually a gas that's really, for the most part, free ions and free electrons. So as you pass by, for example, a polar crater, the electrons will actually fill into the crater ahead of the ions. Now, as it turns out, as it does that, you create an electric field. It's called an ambipolar electric field, and that electric field then drives in the ions.
These hidden troves of water ice and other volatiles in the polar craters may be protected by a dangerous electric charge of hundreds of volts.
3, 2, 1, 0, and liftoff of the Delta II with Grail. Journey to the center of the moon.
Grail consisted of two probes called Ebb and Flow. Linked together in a single flight path, they studied the gravitational field of the moon, generating maps like this crustal thickness atlas. It reveals much about the interior of the moon and even has some surprises.
2 years ago, we reported evidence that the moon is shrinking. Now we've found evidence that the moon is actually being pulled apart, forming features called graben. So the shrinking moon, it turns out, is not shrinking everywhere. Some places the moon is actually expanding by a little bit. So finding these young graben was a real surprise because we thought, well, all these lobate scarps are telling us the moon is shrinking. So what are these little small graben that are telling us the moon is pulling apart doing in this picture? How does this all fit together? All that's related to how the moon has evolved, how the moon has lost heat over its 4.5 billion year history. Most of the terrestrial planets, when they formed, were very hot, and they got so hot that they actually completely melted. When that happens, they will be in a general state of contraction because they're still hot on the inside and cooling down, and as they cool, they want to shrink. Only the outer part of the moon melted, forming what is called a magma ocean. And in that model, the balance of stresses or forces that are acting on the moon would allow us to form both these small lobate scarps that show contraction as well as these small graben that show the moon being pulled apart. One of the really, really exciting returns of the Lunar Reconnaissance Orbiter mission is that we've seen this now growing evidence of very young geologic activity on the moon.
The moon's crust is much thinner on the near side, 68 kilometers thick on average, and varies from less than a kilometer under Mare Crisium to 107 kilometers thick just north of the crater Korolev on the lunar far side. The moon's mantle is only partially molten, and the moon's center of mass is offset by about 2 kilometers in the direction toward the Earth. This and other data quickly changed our understanding of the moon. To gather more evidence on the unusual electrical properties on the lunar surface and how it affects lunar dust, NASA sent LADEE, the Lunar Atmosphere and Dust Environment Explorer, to investigate.
At higher altitudes, we saw very few dust particle impacts, but the lower we went with LADEE, the more we saw, and it's a very, very steep rise. So if you're operating with spacecraft very close to the surface of the moon, as you would with a robotic lander or a human lander, you might need to consider the fact that you've got more dust there in the way as you come in.
This probe flew progressively lower and finally impacted on the surface.
Ignition, throttle up, main stage.
This is Morpheus, a robotic self-guided lander. You tell it where to land and it will do the rest, independently seeking the safest course and avoiding any rocky dangers. The ESA were also developing an autonomous lander to perform the same function.
The lunar lander is a small but very challenging mission. The most important part of it is, of course, landing on the south pole of the moon, which requires innovative solution concerning landing, hazard avoidance, navigation, and in fact, this is the mission which will bring about the new generation of navigation and guidance sensor, algorithm, and software.
But a fiscal year is a long time in space. NASA now have little interest in returning men to the moon. They are firmly focused on a Martian landscape. The Europeans have had budget cuts. The ESA lander now shelved for the time being. This leaves the door wide open for Russia and the younger players, China, India and Japan, plus several private companies now developing the same technology to put first robots, then humans on the moon. All this time, the Chinese National Space Administration, or CNSA, had launched 2 orbiter reconnaissance satellites, Chang'e 1 and 2. Then Chang'e 3 deposited a lunar rover on the surface. Their latest, Chang'e 5, made a return trip around the moon. They are firmly set on a permanent manned lunar base.
I think the reason this has resonated with so many people and all over the world, it's not just our country, is because everyone can look up in the sky and see the moon. And I think a lot of people remember the Apollo landings, the first, man on the moon, and you can also look up at the sky, and I believe that people, it's very tangible to them that way. The moon, they can relate, and so they want to be a part of it. That's my theory on why people have just so connected.
The moon is indeed a tantalizing prize. The Chinese have their lander and rover there now. Japan and India will be next. South Korea has an interest along with Russia, Canada, France, Italy and the United Kingdom. Private enterprise has had a prod with the Google Lunar X prize. The $30 million prize pales beside the glory of being the first private company to land a robot on the moon and to explore at least 500 meters and transmit high-definition images back to Earth. So far, there are 4 hot contenders. The Barcelona Moon Team, a consortium of companies headed by Galactic Suite Design. Their interests lie in space technology and industry with a strong focus on tourism. Penn State Lunar Lion Team. Faculty and students are developing a spacecraft to land on the moon, then lift off again and relocate to fulfill the prize requirements. Moon Express is a group of space and Silicon Valley entrepreneurs looking to mine the moon for its valuable resources like platinum, titanium, and the rare isotope helium-3. Finally, Astrobotic Technology, a Pennsylvania-based company with support from other companies including Alcoa and Caterpillar. They have already reserved a launch on a SpaceX Falcon 9 launch vehicle. Getting to the moon is one thing, staying there is another.
It was one thing to go for a handful of days in Apollo and go when you knew that the sun was quiet, or you hoped the sun stayed quiet, and you took the risk, you calculated the risk of cancer and such, and you made a short mission. If you're going to live there longer, you need to understand it well enough to go, here's what I need to do to protect myself.
One of the things that we're looking for in the LRO mission is how the high radiation environment affects our ability to explore. So if we bring cameras or communication devices, how will they be impacted by the cosmic radiation? We need to protect our equipment as well as ourselves.
We want to be able to go back to the moon so that we can live there for long periods and work on the moon. So we need a mission that can help us find the best places to go and determine how to go back there safely.
Access to solar power continuously, that may be the first and most important reason over the near term. And then the possibility of resources being there. Those may take a much longer time before we're able to really exploit those, but the solar power is something we can exploit right away.
Whether it's water ice to have water, or potential minerals that we could use as raw materials to make into things that we would need.
All the major players have designed and planned many varieties of lunar bases. NASA, ESA and private contractors have concepts on the drawing board. As more information comes in from the lunar satellites on the environment, resources and dangers of cosmic radiation, these plans evolve. One of the latest is to use 3D printing technology. With all the challenges and difficulties, many have made firm commitments to establishing bases within 10 to 15 years. Some for scientific research, others for commercialization and tourism. Some would choose not to send test pilots and scientists, but stewardesses and sommeliers.
When we look back on what we did in LRO and If we look at what followed, I think we'll see a profound impact. We'll see us as really being the small first step where we have human beings permanently off this planet, beginning to move out into the solar system, starting with the moon. As that pans out, I think we'll be a small piece of a profound development that when history looks back, say this time we went back to the moon, this time we stayed, and we moved on from there.
As we continue to study the moon, our understanding of it improves, giving us new insights not only into how it has evolved over time, but also how other rocky planets in our solar system have come to look the way they do. With new missions, new instruments and new technologies, we will continue to improve our knowledge of the moon and better understand the history of our solar system. Launching payloads into space is no straightforward matter. Historically, rocket launches have been used as the proverbial swords into plowshares. Missiles designed to carry atomic warheads now send satellites and probes into the solar system. Ironically, it's one of the few exploits mankind undertakes that doesn't occur in nature. Rocket science is all it's cracked up to be. Bringing together the mathematical, engineering and mechanical skills required to design, build, test and successfully launch a rocket into space is a mammoth technical undertaking. So many countries and corporations have the capacity for launches nowadays that they appear commonplace.
0.
Only the keenest science geeks seem to watch them these days, unless, of course, something goes wrong, and then everyone is hooked. Space launchers fall within several categories, based on their payload or cargo weight and where it needs to get to. The unsung heroes are the commercial satellite delivery systems, providing light and medium lift capability to low Earth, polar or geosynchronous orbit. Many countries such as Argentina, Iran, North Korea and Ukraine boast their own homegrown systems. Even New Zealand, in a joint venture with the US, is developing a budget CubeSat launcher called Electron. The Soviet Union, first to harness its ballistic missiles, has several workhorses like the Proton rocket family, the Rokot, Zenit, Dnipro and sea-launched Volna systems. Ukraine in its current form inherited some of these rocket systems after the Soviet breakup. Like the Proton, these systems use highly toxic fuels. They will be phased out by 2030 and replaced by the Angara rocket system, which is both environmentally friendly and modular in construction to save launch costs. The Angara rockets are designed to put payloads ranging from 3,800 to 24,500 kilograms into low Earth orbit. The Russian Soyuz rocket, designed in the 1950s, has proved to be the most reliable rocket system ever flown. Upgraded to version 2, it will continue to operate alongside Angara. The Russians are also looking to develop a replacement for their aging Soyuz TMA spacecraft, with several designs already on the drawing board. Japan has its Epsilon satellite launcher, which can lift 1.2 tons into orbit. Their H2 continues to evolve, the B variant delivering cargo missions to the ISS.
Ignition. And liftoff. Liftoff of the HTV on a journey to the International Space Station.
補給機コウノトリ4号機を搭載した H2B ロケット4号機は平成25年8月4日午前4時48分46秒に種子島宇宙センターから打ち上げられました。
India's ISRO space organization has developed a range of vehicles for delivering satellites, either to polar orbit with the PSLV or geosynchronous with the GSLV Mark II. India has big plans for space development, one of which is to build a man-rated capsule. The Chinese Long March series of rockets has made steady progress and powers China's manned space program. Even they are becoming environmentally conscious as well. The Long March 5 heavy thrust cluster rocket, with a loading capacity up to 25 tons, is by far the largest carrier rocket China has.
Compared with previous rockets, the biggest difference is the non-toxic propellant in hydrogen-oxygen engines and LOX kerosene engines that will not pollute the environment. And we applied serialization, unitization and modularization to design and manufacture.
Another major player in launch capability is the European Space Agency ESA, with its facility at Kourou in French Guiana. The Vega launcher, developed by ESA and the Italian Space Agency, continues to operate for light payloads. The real European success story, however, is the Ariane 5 heavy lifter, the workhorse for ESA and the CNES. But it too will shortly be replaced by Ariane 6. Currently under development, it will use components in common with the new Vega C rocket.
Ariane 6 will reduce the cost of our launch service by 50% compared to today. So you have to realize that in just 4 years, we are reducing the cost of a launch service in Europe with 50%. And that is, of course, a major step. And if you think about Ariane 6 in a double launch configuration, we are able to offer a price which is really, really attractive, also in comparison with the competition. So the situation that we will have with Ariane 6 and Vega C will be exactly the same in terms of what we can launch as we have today with Vega, Ariane 5 and Soyuz. We can launch every satellite with these two launches in the future. It is very clear that the international competition is getting more and more intensive. This is very clear, especially from the American side. We can see that there is a systematic, let me say, aggressive approach of the market to gain market share by American suppliers of launch services.
When NASA, intent on pursuing the Orion and SLS deep space system, relegated low Earth orbit to the private sector, the commercial floodgates were opened. The United Launch Alliance took over the existing NASA hardware and services and now operates the venerable Atlas V, along with the Delta II and heavy lift Delta IV systems. It's now developing the Vulcan rocket for future expansion.
We have main engine ignition, 2, 1, and liftoff. Liftoff of the United Launch Alliance Delta IV Heavy rocket carrying the NROL-37 mission.
The Vulcan Centaur vehicle will be a high-performance, lower-cost, best value vehicle. We're going to maintain our mission success history that we've had with Atlas and Delta. So we've got two main engine suppliers, Blue Origin with the BE-4, which is a natural gas-powered engine, and we've got the AR-1 from Aerojet Rocketdyne, that is the RP-1 configuration. Both of those teams are making good progress. We've been through CDR with the Blue Origin engine. We've been through PDR. They're both on a plan to get to engine testing this year, and they're both on a path to support our late 2019 launch date.
With that mission now opened up to commercial ventures, many companies are rushing to build better, safer, and most importantly, cheaper rockets. Two private service suppliers for NASA are Orbital ATK and SpaceX. These are the first two contracted by NASA for current ISS resupply payloads and planned manned transfer missions. Orbital uses Minotaur rockets, which are in reality the MX Peacekeeper ICBM, which was never fully deployed as a result of disarmament treaties. Orbital has modified these rockets to carry scientific payloads. Their heavy payload launcher is the Antares 230 and 232, which can lift 8,000 kilograms into low Earth orbit, including the Cygnus spacecraft. With the Falcon 9, Elon Musk's SpaceX company is working on the principle of recycling or reusing launch systems to make launches cost-effective. They can now return the main launch stage back to Earth and land it safely, to be refurbished and ready to launch again. Working on their heavy lift Falcon, which will be able to lift 54,000 kilos into orbit, or 13,600 kilograms towards Mars, and then return to the launch site for reuse. Even the Falcon Heavy, however, will be dwarfed by the upcoming NASA Space Launch System. It will tower over everything previously seen, with the capacity to put 130,700 kilograms into orbit or send 52 metric tons into deep space. Its first task will be to fly the Orion crew capsule and a probe to the Galilean moon Europa. Sending humans into orbit is another matter altogether. Here, launchers have to be incredibly reliable and able to lift very heavy payloads safely. In other words, they have to be man-rated. The only two man-rated capsules at present are the Chinese Shenzhou and the Russian Soyuz TMA. Unsurprisingly, they look very alike. The Russians, however, are looking to the future and a crowded commercial market. Their Soyuz has successfully flown over 120 missions, but a new, cheaper capsule called Federation is underway. It will carry up to 6 cosmonauts and will be competing against NASA's Commercial Crew Development Program, which has Boeing and SpaceX delivering cargo and soon astronauts to low Earth orbit. Aerospace giant Boeing's space capsule, the CST-100 Starliner, is to ferry astronauts to and from the International Space Station.
Starliners go.
When you're sitting in the capsule on top of a rocket and the final moments of the countdown are happening, it's exciting. It's like being on the top of that roller coaster when you're a little bit scared, but you're really pumped because this is what you've been working for all your life, taking that next step into exploration.
We're over 1 kilometer. Truck deploy. Trucks look good.
California-based SpaceX is developing its Dragon capsule to carry crew to low Earth orbit and beyond. The crewed version of Dragon would carry up to 7 astronauts to the orbiting lab. Blue Origin is a strong competitor to both contractors, but its sights are on the tourist suborbit segment. They too have designed their rocket to return to launch for reuse, and their capsule, the Blue Shepard, can hold 6 paying customers.
Shepard has cleared the tower.
There you have it. There it is, 70,000 pounds of thrust pushing that crew capsule.
The B-3 engine remains on. The booster continues to space.
The drogues are out on the crew capsule. There go the mains. And touchdown of the New Shepard crew capsule. From what we can tell, that was a nominal in-flight test of our escape system. And again, all astronauts on board would have had a pretty exhilarating ride.
touchdown!
What an extraordinary test and a tremendous final flight for both craft.
Their main rival will probably be Virgin Galactic or Vulcan Aerospace with their air-launched systems. Sierra Nevada's Dream Chaser is a small space plane designed to carry 7. The spacecraft is based on a NASA concept vehicle from the 1980s called the HL-20. Having failed to secure a NASA contract, Sierra Nevada has teamed up with Vulcan and European interests to further develop a version of the Dream Chaser. Advances in aeronautical engine design have led to the Sabre.
We're actually at Reaction Engines test site at B9. What is very significant about this is that we are in the process of testing a very, very important development in aerospace propulsion, which is a pre-cooler, a device for cooling the air entering a high-speed engine so that the engine can continue to operate pretty much as normal. This means that we're going to be able to fly at speeds of Mach 5 pretty easily in the future.
It is in effect a rocket engine burning hydrogen and oxygen. That in itself is not unusual, but whilst in the atmosphere the oxygen is taken from the air, cooled to liquid temperatures and fed directly into the combustion chamber, once outside the atmosphere, the engine resorts to the liquid oxygen carried on board, like a conventional rocket engine. Skylon will be powered by 2 Sabre engines and operate like a conventional aircraft capable of flying directly into orbit, transporting 15 tons of cargo into space, and returning for a runway landing.
We're looking at a revolution in transportation equivalent to the jet engine, and access to space, access to anywhere in the world within 4 hours is on the cards. Once you've got access to space on that basis, that's the stepping stone to anywhere in the universe, and a very exciting future for the human race.
Although government contracts are lucrative for these private companies, many firmly believe tourism is the way to fund future space development. For those cashed-up civilian tourists, Space Adventures team has designed a circumlunar mission using a unique combination of existing and flight-tested Russian technology. The combination of the Soyuz spacecraft and the lunar module will provide ample living space for your approximately 6-day journey and the fuel required for you to leave low Earth orbit. Perhaps the most ambitious is Elon Musk's SpaceX interplanetary transport system, helping make humanity a multi-planet species. The initial design objective of the vehicle is to launch a variety of missions to Mars and other destinations in the beyond Earth orbit portion of the solar system. The large payload capacity of the launch vehicle, with the ability to place 300 tons into low Earth orbit, places it into the super heavy lift class. The ITS launch vehicle's first stage is designed to be reusable, following a return to the launch site and vertical landing after each launch. What's new on this vehicle is full reusability of even the second stage and the spacecraft as well. Cheap, safe space travel for all is just around the corner. The orbit between us and our star, hidden within the sun's glare, often visible only at sunrise or sunset. Venus, the first and brightest star in the evening sky, and Mercury fleeting across the solar disk. They are half of our solar system's terrestrial planets, yet we know so little. As we begin to take a closer look at our companions, they are posing more questions than answers. This is Mercury, the innermost planet closest to our Sun. Mercury's days are longer than its years, and it has an elliptical orbit from 47 million kilometers at its closest point to 70 million kilometers. Difficult to observe from Earth due to the Sun's light, Mercury is an enigma of the solar system's evolution.
Well, Mercury is really a weird planet. Normal terrestrial planets, all the rest, have a relation between how big they are and how dense they are. Mercury is not following that rule. It's much more dense than what you would expect for its size. That is not normal, so something went wrong in the formation of Mercury that we don't know.
Only 2 probes have been sent to investigate the planet, and only one has achieved orbit. Mercury is difficult to get to because of its orbital speed and the gravitational influence of the Sun.
Mercury, for us, is a planet of extremes. So you have temperatures like 400, 450 degrees on the surface during the day, and imagine that's like being in a pizza oven on Earth. So it's really hot there, and temperatures at about minus 175 during the night.
Mercury orbits the Sun every 88 days in an atypical elliptical orbit. At its nearest approach to Earth, it is 77 million kilometers away. The first close-up imagery of Mercury came from the US probe Mariner 10 in 1974. With insufficient fuel to slow the craft, it was not possible to put the probe into orbit. Instead, it orbited the Sun, passing by Mercury 3 times. The flybys provided 2 interesting observations. Firstly, Mercury has a magnetic field similar to Earth, which is unusual due to the very slow spin of the planet. Secondly, the surface of the planet showed extensive cratering and very little volcanic or crustal movement. 2 contradictory observations of why the planet has such a magnetic field. The second and most recent probe is Messenger. Launched in 2004, it made several planetary flybys of Earth, Venus and Mercury to slow down to the correct speeds. It took 6.5 years to reach Mercury and enter orbit in 2011.
Because of this short distance from our central star, the temperature of the planet is very, very high. And when you want to fly around Mercury with a satellite, you find yourself in a very special thermal situation where you get a lot of heat coming from the planet itself that behaves like a thermal mirror. And then from the side you get the heat from the sun. So you have 2 heating sources which may destroy a normal spacecraft. Another NASA mission, Messenger, is getting operational in a very loose Mercury orbit because, as I said, the thermal situation is such that you better stay away from the planet.
Its primary mission was completed within a year, mapping the entire globe with about 100,000 images. With fuel in reserve, the mission life of the probe was extended. After 10 years, MESSENGER continued to send back information and observations. Magnetic field data, the magnetosphere, the effects of solar wind plasma, and studies of the atmosphere of Mercury. It is so low in density it is constantly blown off the planet as an exosphere, revealing the likes of sodium, calcium, and magnesium in a trailing tail away from the Sun. Spectrographic imaging of the surface material has thrown up more questions about the high metallic density of the planet. The observations do not fit the standing theories of the planet's evolution, which will have to be completely overhauled. One other interesting detail: at the north and south polar regions, MESSENGER has detected the presence of water ice in the permanently shadowed interiors of craters, just like on our Moon. In 2014, the probe was tasked to fly much closer to the surface, as close as 50 kilometers. There it imaged the surface at much greater resolution, hunting for more detailed signs of the planet's geological history. Left unaided, the probe continued to descend and ultimately impact on the surface. There was, however, sufficient fuel in reserve for 3 trajectory alterations to increase altitude and give the probe a short time extension to continue its work into 2015. A third mission to Mercury is underway by the European Space Agency and the Japanese agency JAXA. Bepi Colombo is named after the Italian mathematician Giuseppe Bepi Colombo, who first developed the gravity assist maneuver for NASA with the Mariner 10 probe. It consists of 2 orbiters, the ESA Mercury Planetary Orbiter and the Japanese Mercury Magnetospheric Orbiter.
What scientists want to do is try to understand the nature of the planet itself. What material is on the surface. We would like to measure temperatures. We would like to see the interaction with the solar wind. Then Mercury has a magnetic field, which is like Earth, a dynamo field. We would like to understand that.
The Japanese MMO will focus on the magnetic field environment around the planet, while the ESA probe will focus on the planetary surface. Like the previous 2 probes, Bepi Colombo will use Earth and Venus to slow the probe's speed down to drop closer to Mercury's orbit. This trajectory will take approximately 7 years to accomplish. With solar electric motors to maintain deceleration, then a conventional rocket engine will be used for orbital insertion. The orbital life of the probes in the harsh environment is expected to last 1 to 2 years. The 2 craft carry a suite of the most advanced instruments, including a laser altimeter and magnetometer, infrared and ultraviolet spectrometers, imaging X-ray and high-resolution stereo cameras. Bepi Colombo is designed to answer specific questions about this planet. Why is the planet so dense? How did it form? Is the planet tectonically active? Why can no iron be identified on the surface? In the absence of any ionosphere, how does the magnetic field interact with the solar wind? How is the magnetic field generated?
We have a theory to understand how planetary systems form. Now, the theory was based on explaining the solar system, and it was fine, it worked. But now, when we have discovered new planets around other stars in the galaxy, the extrasolar planets, they don't fit at all. So something is wrong. And the special cases, those that are difficult to understand in the details, like Mercury, are very helpful.
By finding answers to some of these questions, Bepi Colombo will help us understand how the solar system was formed 4.5 billion years ago. It is the first and brightest star you see at night. Our sister planet in some ways, our closest planetary neighbor in both distance and diameter. However, Venus is difficult to reach and a very strange world when you get there.
In the early days of the solar system, Venus and Earth must have been very similar. But then something happened and they took a different route in its evolution.
Venus is the only planet in the solar system that needs more time to rotate once around its own axis than it rotates around the Sun. There must have been a major disaster in the early history of the planet where it collided with a big other object. And this made it stop its rotation. The problem is that without the protection and without the rotation, the planet lost its water, and so it's completely dry. And this, in the end, led to a horrible greenhouse effect that caused the temperature to rise to the levels that we see
One of the main differences between Venus and the Earth is simply that Venus doesn't have a magnetic field. So the way it interacts with the star is completely different. If you want to understand how did Venus get that way, why does Venus not have any ocean, you need to understand the interaction between the star and the planet.
The Soviet Union and the United States sent probes with some success. 3 Mariner spacecraft made brief flybys, and the Soviet Veneras entered the atmosphere and touched down, some surviving for minutes. They managed to send back tantalizing images of an almost serene vista. NASA sent 2 more probes, Pioneer Venus 1 and 2, the latter depositing 5 small probes onto the surface. The Soviets continued their program of Venera probes with 4 successful landers and orbiters. A further 2 Russian Vega missions deposited atmospheric probes as they swung by en route to Halley's Comet.
The atmosphere of Venus is incredibly interesting because it's so different from the Earth's atmosphere. And we'd like to understand what causes these differences, because this might well help our understanding of climate change on planet Earth.
There's a very dense atmosphere, to 97% of carbon dioxide, a very strong greenhouse effect, and the temperature down on the surface is more than 450 degrees Celsius. And the surface pressure is 92 bars, it's almost 100 times more than the Earth. So it's a very, very unpleasant place to be.
High up in the clouds, about 100 kilometers from the surface, the wind speeds are very, very high. The wind is traveling at 300 kilometers an hour, and it travels around the Earth, around Venus every 4 to 5 days. So that's one of the things we don't understand, why at the surface the winds are very gentle, and high up the winds are very, very fast. So it's a very different atmosphere to the Earth's atmosphere.
0 and liftoff of Space Shuttle Atlantis.
In 1989, the NASA probe Magellan was launched from the payload bay of Atlantis en route to Venus, its 5-year mission to radar map the entire planet's surface. The radar managed to peer through the dense atmosphere and revealed the true face of Venus. What it showed was a young surface with few craters and mostly covered with volcanic activity, lava flows and large lava plains. Surprisingly, there was little evidence of wind erosion, and the surface plate tectonics were dominated by global rift zones, unlike Earth. To date, that was the last Venus probe from NASA. It was 12 more years before Venus came under scrutiny again, this time by ESA's Venus Express. To conserve fuel for a long mission, the probe utilized aerobraking in the Venusian atmosphere to make orbit.
Very interesting discoveries of Venus was a huge vortex, a huge cloud at one of the poles of Venus that in some ways looks very similar to a hurricane on the Earth. But this is a long-standing event that's there all the time. We don't understand how it's formed, why it's there, and how it will evolve.
When we arrived at Venus 8 years ago, we detected winds at 300 kilometers per hour, very fast. But what has happened during these years, until now, they have actually increased. We now see winds of 400 kilometers per hour. And we can't really explain why that has happened.
More questions were raised by the planet's absent magnetic field.
Venus doesn't have a magnetic field. So Venus is just this big rock with this atmosphere and the ionosphere sitting in space, and the supersonic solar wind with the interplanetary magnetic field whacks into Venus, and it can't penetrate through the ionosphere. So the interplanetary field lines just sort of pile up ahead of Venus, like cars on a freeway. This solar wind whacking into it essentially sort of strips off the atmosphere, and it literally forms this long tail, like a comet that's stretching out into space. Pioneer Venus Orbiter was the first spacecraft to really thoroughly explore that night side region where the atmosphere is all escaping away, and it discovered this really mysterious phenomena which has yet to be explained. Imagine that we're flying from pole to pole on the night side, so we're feeling the plasma around us, and then suddenly the ionosphere disappears, and then it sort of comes back. And this is what an ionospheric hole is. It's like a chasm in the sky, a big hole where the ionosphere is just absent. So Pioneer Venus Orbiter basically measured inside these things, and we saw that there is very little plasma, and there's all this magnetic field. And from that, they sort of suggested that this is essentially a magnetic structure that's sitting in the night side. I wanted to see if I could go looking for these things with Venus Express. What we saw is essentially this really exciting, strong, straight magnetic field lines that we expected, and really boring plasma signatures. It shows us that this is a magnetic structure, right? This is a tube of interplanetary magnetic field that, well, PVO saw it coming out of the ground, and now we've seen it way out in the tail. So these things really continue out to much higher altitudes than we previously have found them at.
As Venus Express neared the end of its mission, scientists made some risky aerobraking maneuvers to bring the probe much lower in orbit to make close-up observations of the planet. These maneuvers involved daring plunges into the hostile atmosphere only 130 kilometers above the planet's surface.
For the aerobraking, we wanted the most area possible to get the most friction possible, but that also generates heat. And so what we did was we went into the atmosphere in this direction, because this face of the spacecraft, which had been attached to the rocket originally when it was launched, was most able to take the forces and the temperatures. We also turned the solar panels so that the side with the actual solar arrays was in the back to maximize the area as we went through the atmosphere to maximize the amount of friction and to get the most amount of braking. What we saw that was a little unusual is the variability in the pressure, as if there were waves within the atmosphere. And so that possible wave-like structure was not expected, and analyzing that data will keep scientists busy for a little while yet.
Venus Express carried a suite of 7 instruments: magnetometer, spectrometer, and several cameras to study the atmospheric winds and surrounding space environment. Venus Express outlived its planned 2-year mission by another 7, and only recently was it directed to ditch into the planet's atmosphere. The Japanese have made the most recent attempt to reach Venus with Akatsuki, whose planned observations are to include cloud and surface imaging with infrared cameras. Their main focus is the Venusian meteorology, including confirming the presence of lightning and any current volcanic activity. The probe failed to enter orbit on its first attempt, and JAXA are hopeful when the probe's heliocentric orbit returns it to Venus that a second attempt will succeed very soon. There are many plans afoot to return to Venus. Even a manned mission has been studied by various groups. One such study conducted for NASA produced HAVOC, a high-altitude Venus operational concept. It would rely upon 2 spacecraft sent into Venus orbit, the first unmanned atmospheric descent stage and the second orbital return craft carrying the crew. They would dock, transfer crew to the descent stage, and proceed to deorbit. Once into the upper atmosphere, a parachute would deploy, slowing the descent and allowing the deployment of a dirigible craft to inflate and carry the crew at high altitude. From there, they would study the planet below. The return journey for the crew would begin with a high-altitude launch back into orbit, where they would dock with the orbiter, transfer crew and equipment, and then make the journey back to Earth. There they could dock with an Orion capsule for the return to Earth. The International Space Station is without question the jewel in the crown of low Earth orbit. Observation post, research lab and classroom all in one. But many other assets orbiting Earth are even more important to our everyday lives, delivering communications, weather observation, global positioning and resource management, and the list is growing every year. chances are you are watching this program via satellite in one way or another, either transmitted directly or indirectly to your television, iPad, laptop, or phone. In other words, you're using technology once considered science fiction. Pushing the envelope, technology must keep up with demand. More data, more reliability, and real-time connection. Space destined hardware and technology are on the cutting edge of science, often introducing new methods of gathering scientific information. Demonstrator missions are regularly sent up, flying new engineering solutions to prove the hardware in situ, even without a specific goal in mind.
Technology goes through a whole development cycle, which we call the seamless chain of innovation. We start from the idea and we work along to develop it through our work in the labs, through the work of industry, and especially of small and medium industries, which are the vectors of innovation. But at the end, you need to prove that it works in the real place, space. And in order to do that, we use these missions that can take the risk of flying unproven technology and demonstrate to the larger missions that they work.
Research laboratories focusing on the next generation of space hardware are dotted around the globe. The UK's Space Gateway Harwell campus, the ESA RAL Advanced Manufacturing Laboratory, supports cutting-edge research and development.
The purpose of the laboratory is basically to assess and pre-screen candidate materials and processes for future space missions. So this will guide ESA, as well as the space community, in focusing their technology investments in the right area.
The lab has extensive on-site testing facilities, such as the ISIS neutron source, the Diamond Light Source synchrotron, and the UK's Central Laser Facility. This year will bring the first launch of a satellite using the small GEO platform, Hispasat 36W1. Small GEO, a telecommunications platform accommodating a wide range of payloads and missions, has been developed in Germany in a public-private partnership between ESA, OHB, and the operator Hispasat.
It indeed, because Hispasat and ESA were able to join forces, that we were able to develop a satellite with such a level of innovation. On the one hand, a new platform with a new satellite prime contractor, on the other hand, a payload embarking also a high level of innovation. And altogether, this satellite has been developed, is going to be flown, and we provide very innovative services. So end-to-end, the level of innovation is very high, and indeed, separately, neither Hispasat nor ESA would have been able to undertake such a complex development. With the small GEO, what we have tried to achieve was really to develop a new product in the low end of the telecommunication market. And at the same time, this new product would allow a new prime contractor to become a prominent player of the satellite telecommunication market. That's the OHB, which is the prime contractor of this satellite.
This is a class of satellites that only have electric propulsion on board, which is a high-efficient system that allows achieving important mass savings. So we are able to put in space a satellite with a similar capacity of a full chemical one, but with much lower mass, which means less launcher cost, compatibility with more launch vehicles. And again, this translates in advantages for the operators who have at their disposal more efficient technical solutions for their mission. But it's very flexible, so it can also be used for other geostationary applications.
Another scheduled event in the telecom area is the launch of EDRS-C, expected by the end of the year. EDRS-C is also based on the Small GEO platform and will be the first dedicated satellite for EDRS, the European Data Relay Service. It will be the second element of the Laser Relay's Space Data Highway. Low Earth satellites encumbered with line-of-sight communications can beam their data upward to geosynchronous satellites via laser, which can then transmit the signal to ground stations at any time.
The Small GEO program is just the first step for OHB. OHB has already sold a number of other telecommunication satellites, and indeed this is the start of a product line that will evolve over time, like any other product lines of the other prime contractors operating in the satellite telecom market.
Another area of research has been in cost and time effectiveness in developing satellites. This has led to the CubeSat, several of which have flown in space. Measuring just 10 by 10 by 10 centimeters, these small cubes or nanosatellites have become extremely popular, opening up new possibilities for a wide range of groups previously unable to access space.
We are a small group of students with 2 professors and 2 coordinators, and we had 52 students who did the master's thesis on this project.
It's a great project for the students because it's the occasion to apply practical stuff and not only the theoretical stuff they have learned at school.
Our satellite is the telecommunication satellite. We use the D-Star protocol for the radio amateurs to communicate around the world.
This is really a special moment when we can see that finally the Peoples is installed on the platform that will carry it to space on board the Soyuz launcher.
So it's a great feeling to be here in Kourou, in French Guiana, with the satellite almost in space and normally ready to roll.
Using off-the-shelf technology, CubeSats have been launched from the ISS and piggybacked onto other satellite launches. They will soon be deployed to Mars, asteroids, and further afield. GPS is used every day by people on the ground thanks to global positioning satellites from the United States. But GPS is not the only system in orbit. Russia has its GLONASS constellation, China has its own Beidou system, and Europe is building the Galileo network.
The initial services is a stage in the program whereby there is sufficient infrastructure is made available in space, satellites around the globe who circle around, plus infrastructure on the ground which control the satellites, provide the navigation signals. Enough of that infrastructure is ready so that the system can be used. The use is still not fully 100%, hence the word initial services.
These constellations are not exclusive. Galileo will also use the GPS system for even more accuracy, and the US is tying in with the Russian GLONASS for extraterrestrial services. In other words, they will enable spacecraft to utilize the positioning system in almost any orbit around the Earth.
Some of the signals are available only during a certain percentage of the day. The satellites move around and not all of the day you have sufficient satellites inside. But there is enough to start. And this is a very important moment in the program, an excessively important moment, because this actually shows to the world that the system is really going well. The performance we actually can provide, we know, is excellent. And of course we will continue building out the full constellation, but the users can actually now start using the satellite system.
The European Galileo navigation system is nearing completion. More satellites will be launched this year, adding to a constellation which will eventually number 22.
Under initial services, there will be 3 services provided. One is the so-called open service. This is for the mass market. This is where people will use their smartphones, their navigation devices in cars, which will have Galileo-enabled chips inside, which will receive both Galileo and GPS in combination, and it is the combination of the 2 systems which will be used to determine the position of the user. For ESA and the European Commission, when we started with satellite navigation, it was of course not quite clear how really important satellite navigation was going to be. And we had studies, we had our insights in it, and we knew that it would be important. But now we really see how important it is, particularly looking in the future, where we're going to need to have a sufficiently developed satellite navigation infrastructure to support autonomous driving and all sorts of other applications.
NASA has already developed specialized GPS receivers for space application. The Navigator receiver from NASA's Goddard Space Flight Center first flew in 2009 and proved to be very successful. A number of future missions in HEO, GEO and MEO plan to work with this receiver using its high-sensitivity signal acquisition and tracking capabilities. NASA's JPL has also developed the Blackjack flight GPS. Now being flown aboard an Argentine satellite, the system looks at how the GPS radio signal is distorted or delayed along its path. A typical GPS signal can plot a position to within around 22 yards. Blackjack can pinpoint its host satellite continuously to an accuracy of about 1 inch. 18 receivers are on orbit, while another system under development called the Triple GNSS or Tri-G will be able to track GPS and GNSS signals, including the Russian GNSS and European Galileo navigation constellations. All of our spacefaring nations continue their Earth observation work in collaboration with a number of organizations. The refinement of orbital positioning and unhindered high-speed communications mean more new technologies craft are being added to the armada of observation satellites. They include Europe's Copernicus program with no fewer than 3 Sentinel satellite launches. In March, Sentinel-2B will be launched carrying a wide-swathe, high-definition multispectral imager. With Sentinel-2A already on orbit, both Sentinel-2 satellites will monitor land cover, vegetation and water pollution.
Now that we get Sentinel-2B to fly together with Sentinel-2A, there's a couple of improvements that we get so far. We have a revisit of 10 days. With Sentinel-2B, we will have a revisit of 5 days. That means we see every spot on Earth every 5 days. That will help, of course, also to avoid the clouds or to have the chances higher to have no clouds in the various regions of the world. Both together, Sentinel-2A and 2B will also improve the performance of the services that are using the data.
Sentinel-2B is contributing to a constellation of Sentinel satellites, which really provides data over decades in different domains and with different instruments on board. So therefore, we're building up a fully operational system, which is enough incentive for industry to invest and to rely on this information in the future.
Sentinel-2A is already supporting a lot of applications. They're ranging from, for example, agricultural applications where we can do yield forecast to forest monitoring where we, for example, see deforestation. And besides that, there's plenty of other applications like inland water where we can look at the quality of the water. We can support river monitoring, but also coastal areas where we look at the changes in the coastal regions. On top of that, we recently changed also to acquire the Antarctic region, so we're also now looking at ice and glaciers.
Later in the year, 2 more Sentinels, Sentinel-5P and Sentinel-3B, will follow. The Sentinel-5 precursor mission is a satellite dedicated to monitoring our atmosphere at a high temporal and spectral resolution. It also offers increased cloud-free observation.
A second satellite, which is a replica of the first one, is of course shorter to develop and to test. The main effort when you develop a new system is put on the first spacecraft, where you discover basically all the early problems in equipment production, software validation, integration and test. All the specifications, plans, test procedures are ready whenever you start building your second spacecraft. And this is, of course, a large benefit. The second spacecraft, let's say, was realized in 1.5 year time. The cost as well, of course, of a recurring spacecraft is much cheaper than a proto-flight spacecraft. You could say basically it's 50% of the price of the first one.
Sentinel-3B is a multi-instrument mission to measure sea surface topography, sea and land surface temperature, and ocean and land color.
We are addressing a number of issues that relate to the development of new science, but also operational missions. For example, Earth Explorer missions, the scientific missions, but also we are preparing the next generation of Sentinel missions for Copernicus. In the next 5 to 10 years in Earth observation, we will face a number of challenges, some of them coming from outside. Big data, constellations, commercial companies entering our domain. And I think there we really have to see, as ESA, as European Space Agency, a public institution, how we can best react to these external challenges and position ourselves with our programs to really address these challenges from our perspective.
Demonstrating new laser technology, ESA is launching the ADM Aeolus satellite. ADM stands for Atmospheric Dynamics Mission. It will provide global observation of wind profiles. With this mission, ESA hopes to further our knowledge of the Earth's atmosphere and weather systems. Space is a hazardous place. A key part of maintaining reliable satellite services is keeping a weather eye out. The Earth is constantly being bombarded by damaging solar storms and charged particles ejected from the Sun. These could knock out satellites and even communication systems and power grids on the ground. Geomagnetic storms, solar X-ray and proton flux, coronal mass ejections and sunspots, all are monitored continuously. The Earth is also surrounded by a cloud of debris from 60 years of human space activities, space junk which could also damage satellites. Near-Earth objects also threaten the Earth and could collide with our planet. All these threats are monitored under ESA's Space Situational Awareness Program, which the Operations Directorate hopes to see continuing to evolve.
want to protect our assets in orbit and on Earth against impacts from space, may it be from space weather or risks from near-Earth objects. And we also want to protect our spacecraft in orbit from risk, for example, coming from space debris.
The Interagency Space Debris Coordination Committee, or IADC, is a forum of 14 nations brought together to exchange information and to research various aspects of this problem. Numerous working groups are studying methods of protection and threat mitigation. No matter what hardware is orbiting Earth, it can only make scientific observations. Only our human perception of the beauty that lies below can help us fully appreciate the planet we call home. Mars, the god of war and the source of man's science-fictional demise. It has fired our imagination for thousands of years. We know the dry, barren planet was once flowing with vast reservoirs of water, the sky thick and filled with clouds, and the tantalizing possibility of life. It is the only other place in our solar system that man might one day call home. We Earthlings have fired numerous probes and satellites towards the Red Planet. An invasion of sorts, not for conquest, but for knowledge. What happened to Mars? Is there or has there ever been life on the planet?
A fundamental question that needs to be answered is life as we know it on Earth, even the simplest type of microbial life, unique? If we were to go to Mars and we were to find evidence of early microbial life, or maybe even present life that somehow survived in the near surface, would it be the same as the early life that developed on Earth? That's a very fundamental question. Does life emerge generally in planets where the conditions for life are favorable if we find out that they were favorable on Mars, or might life take its own unique path in different environments and turn out differently?
We have bombarded Mars with satellites and landers, but there have been more failures than successes. The Soviets established 2 Mars orbiters, while NASA landed 2 Viking landers carrying complex analytical laboratories and searched for signs of microbial life. Their findings were inconclusive. Further missions to Mars still had a high mortality rate, but the successes were outstanding, with robotic probes operating for years beyond their initial missions. In fact, Mars is a planet occupied solely by robots on the surface and satellites peering down from above. All these instruments perform admirably in their specified fields of endeavor, giving us a much clearer picture of the planet and its history. The science was following the water, what happened to it, and where it is now.
Thanks to the specific instrumentation on board the mission, we are able to tell us what kind of ice did we find. And the result is that there is a mix of CO2 ice or carbon dioxide ice and water ice. And it's very important to characterize it, especially for the water ice or frozen water, because one of the main objectives of any mission to Mars is to trace the water on Mars in every form, liquid if possible, solid, water vapor. So it's very important to study the ice because it's one of the reservoirs of water on the planet.
The science was conclusive. There was water on Mars. There were ancient lakes and rivers, even an ocean. We needed to learn more. With the advancement of analytical technology, computer power and robotics, a new rover was constructed. Big, complex and heavy, it required a new way to land on Mars safely. Engineers came up with a system that couldn't be fully tested here on Earth. It required a lot of things to happen correctly, on time and in order. This was the Sky Crane, and the rover Curiosity was the first to try it out. A controlled re-entry with heat shield, aerobraking with a parachute, all pretty standard. Then a rocket-powered Sky Crane drops from the aeroshell and gently descends toward the surface, spooling out the rover below on cables. The rover touches down, cuts the cables, and releases the Sky Crane to fly off and crash harmlessly. The Curiosity rover has been an astounding success, traversing the terrain for over 10 years, taking samples, drilling and studying rock formations, zapping samples with a powerful laser, and photographing its progress.
Now, in the belly of that rover is an instrument called SAM. It's an instrument suite that has a couple different instruments in it that allow us to look at different types of gases. It helps us understand the chemical composition of the atmosphere and the end of minerals that might be found in the rocks and the soils on the surface. In particular, it helps us identify organic molecules that might be present.
So the sort of evidence we're looking for, sorts of signatures of past life that we would be looking for would be signatures of microbial life. So not realistically looking for dinosaur bones and that kind of thing. If life ever existed on Mars, we expect it to have been microbial, microorganisms.
Orbiters, including Mars Odyssey and Mars Express, have been hunting down life as well from orbit.
After 10 years of mission, we have achieved a global view of Mars, and then we know at every location on the surface if you find some special minerals or not. So we have really the global view that tells us the history of Mars. Mars Express has, for the first time, detected methane, and also the concentration in the atmosphere vary from a place to another, from a season to another. And this discovery has been very debated in the scientific community because, in fact, methane should not be there because it's being destroyed in the atmosphere by the ultraviolet radiation.
So if methane is there, there must be a source of methane, and for the time being, the origin of this source is largely unknown.
However, with Curiosity prowling around Gale Crater, it too detected seasonal methane.
Now, methane has been found previously in the Martian atmosphere by both Earth-based telescopes and spaceborne orbiters. But this is the first time that we've actually seen a sharp increase and decrease in the abundance of methane in the atmosphere in Gale Crater. And what this really means is that present-day Mars is an active environment.
The big question is, what is the origin of this methane now being released? The two principal areas are first, by analogy with the Earth, it could be released and produced initially primarily by biology. This would be microbial activity acting on certain chemicals below the surface and then producing methane as a byproduct. But of course we can't state with certitude that it is biologically produced. And so we also consider geochemical mechanisms in which carbon dioxide is actually combining with water and producing methane under very high temperatures and pressures. And that methane can then be released in the atmosphere separately.
Now, at this point, we don't have enough evidence to tell us whether or not the organics we're finding are biological or non-biological in origin. There are several viable non-biological explanations, including this organic material could have come down from space, from meteorites or comets, or organics can be formed by geological reactions in the rock itself. Now, what's exciting about this discovery is it gives us new hope in the search for chemical evidence of life. We found the organic material. Now, the next step is trying to figure out what its origin is.
Main engine start, ignition, and liftoff of the Atlas V with MAVEN, looking for clues about the evolution of Mars through its atmosphere.
The latest NASA orbiter mission is MAVEN. Launched in November 2013, it made orbit 10 months later.
MAVEN is the Mars Atmosphere and Volatile Evolution mission. Our goal is to study the role that loss to space has played in the history of the atmosphere. Where did the water go? Where did the CO2 go from the early planet? These are important questions to understand how Mars went from an early warm, wet environment to the cold, dry environment we see today.
There's evidence of water flowing on Mars at one point in time, perhaps even oceans on Mars. And what happened that it's so barren at this point in time? And a key part of that is the atmosphere, and it's a much thinner atmosphere than what scientists believe it was at one point in time. So the stripping away of that upper atmosphere, that's what MAVEN is going after, the climate change at Mars.
One of these processes is called sputtering, where atoms are knocked away from the atmosphere due to impacts from energetic particles. The sun constantly emits high-energy photons. When these enter a planet's atmosphere, it can crash into a molecule, knocking loose an electron and turning it into an ion. When this happens in the presence of a magnetic field, the ions are captured and spin around the field. Conveniently, the sun generates a giant magnetic field that is carried by the solar wind. As the magnetic field sweeps past the planet, these ions are carried away. Depending on where they form, other ions will not be carried away but will hit the top of the atmosphere. These ions crash into other molecules and fling atoms everywhere. Some of these atoms can be knocked or sputtered into space, causing atmospheric loss. As this process continues over billions of years, Mars' atmosphere has disappeared, and along with it, the water. How much water has Mars lost this way?
We used the world's 3 major telescopes for infrared astronomy. From the ground, we could actually take a snapshot of the whole hemisphere of the planet on a single night.
Water naturally carries a heavy isotope of hydrogen, deuterium, which remains trapped in the water cycle while normal hydrogen is lost to space. Detecting the amount of deuterium enrichment tells us how much water has been lost.
Now we know that Mars water is much more enriched than terrestrial ocean water in the heavy form of water, the deuterated form. Immediately, that permits us to estimate the amount of water Mars has lost since it was young.
So in the ancient past, we have some indications of water was flowing on the surface, but how much water was there? We're talking about oceans, are we talking about small rivers, little rain? So these definitions of how much water was on the planet was very undefined.
A major question has been how much water did Mars actually have when it was young, and how did it lose that water?
The findings indicate that only 13% of an ancient ocean remains on the planet today, now stored in the polar ice caps. 87% of this ocean has been lost to space. This means that early Mars would have looked much different than it does today, with a significant portion of its surface covered by water.
So the really interesting question is, could it form a sea or an ocean? And indeed, it would. In the northern plains, which is a relatively flat region but depressed from the rest of the planet, it would form an ocean that was approximately 20% of the planet's surface area. And so that is a respectable ocean.
This ocean had a maximum depth of around 5,000 feet or around 1 mile deep. It's deep, not as deep as the deepest points of our oceans, but comparable to the average depth of the Mediterranean Sea.
By combining Martian topography with the new estimate for water loss, the researchers were able to simulate Mars's ancient ocean and its escape to space. As Mars lost its atmosphere over billions of years, it lost the pressure and heat needed to keep water liquid, causing the ocean to shrink and recede northward. The remaining water eventually condensed and froze over the north and south poles, giving Mars the ice caps that we see today.
We now know that Mars was wet for a much longer time than we thought before. Curiosity shows it was wet for 1.5 billion years, already much longer than the period of time needed for life to develop on Earth. And now we see that Mars must have been wet for a period even longer.
It's fascinating that we can learn so much about 4.5 billion years ago what measurements are taken right now. And ultimately we can conclude this idea of an ocean covering 20% of the planet, which opens the idea of habitability and the evolution of life on the planet.
Building on this knowledge, scientists are developing the next series of robotic probes to be sent to Mars in the coming years. This time, NASA is building on its successes, utilizing hardware and systems that they know will work.
We've been to Mars before with the JPL Lockheed Martin team. We've been to the surface of Mars before successfully with Phoenix. We know how to operate the arm. The surface operations are much, much simpler than Phoenix. And we're putting 2 instruments on the surface, and then we're leaving them there with no ground-in-the-loop interaction, repetitive, weekly uplink, downlink sessions. We're just made to do this mission.
The InSight mission is a geophysical mission to Mars. It's going to go to Mars and take its vital signs. It's going to take its heartbeat, the seismic activity of the planet.
So we're going to be doing that using a seismometer, a very high precision seismometer, using techniques that have been well developed on Earth to get the understanding of the crust, mantle, and core, and sort of the relationship between those.
It's going to take its temperature by measuring the thermal gradient of the surface, which tells how much heat is coming out.
We also have a heat flow probe, we call it HP cubed. And what that does is it's going to basically take the temperature of Mars, and from that it'll be able to understand what the thermal flux is over the course of a full Martian year.
And it's going to sort of measure its reflexes by looking at how the rotation wobbles with the tidal effects of the sun.
Our final experiment is called RISE, and that's going to be looking at basically the wobble of Mars to help understand what the core size may be in composition.
The European Space Agency is also well along with ExoMars, a rover with advanced drilling capability due to be launched by 2018. Its principal goal? To drill down deep in search of microorganisms.
What is new with ExoMars, with the rover in particular,
is what we call the mobility. Mobility not only horizontal, but also vertical. And this is a peculiar thing that we have on board the ExoMars mission. So we will be able to sample material from below the surface. That is quite important to understand if there is any sign of past life activity on Mars.
We will be looking for the first time in the third dimension being depth. And we think that is where we have the highest chance of making an interesting discovery regarding the presence of organic molecules in Mars.
It's a whole planet out there with a complicated history. That history is a story that's stored in the rocks, and our job is to figure out that story and what that story of that planet tells us about this planet that we live on.
So where Curiosity takes rocks and grinds them up into powder and looks at their bulk constituents, what this mission would need to do is be able to look in a microscopic level and examine the rocks for these very tiny and detailed messages that they would be sending to us about the past life that could have lived there.
This that I'm holding up here is a classic biosignature from the Earth. It's a fossil. We're not actually expecting to see a fossil of shells or other components, but what we want to be able to see are, with this instrumentation, are the fine scale layering that one might see in a rock, in which we can see dark and light toned layers. And those dark and light toned layers are telling a story.
When will NASA send astronauts to Mars?
4, 3, 2, 1. And liftoff at dawn. The dawn of Orion and a new era of American space exploration.
The first test flight of the Orion crew capsule is complete. The hardware and systems are ready for mass production. The components, the engineering, the manufacturing are all underway, with NASA looking back to what worked in the past and utilizing it for the future.
Fire.
The solid rocket booster technology straight from the space shuttle has been extended and tested. NASA's new Space Launch System, or SLS, is coming closer to fruition, reusing the space shuttle's main engines as the new system's workhorses, saving billions of dollars and years in research and development. The Europeans are teaming up with NASA to provide the service model for Orion, allowing for long-duration, deep space flights. Autonomous Martian landing systems are well advanced and being tested. Software and hardware are fully integrated for both manned and unmanned Martian landings. And when they get there,
Desert RAT stands for Desert Research and Technology Studies. This is a group of engineers and scientists.
We're looking to test out new concepts, procedures, equipment like rover concepts to see how they work in the field environment.
So the team tests these technologies to make sure that in future human spaceflight missions we'll be able to do science as best as we can. That's something that NASA's never done, two human rovers at the same time. So we're really trying to develop how do you use these assets at the same time, and interesting things that you might not think about are your communications. So you potentially have 4 astronauts talking all at the same time to mission control or science communication background.
It's just like running a real mission, say, like you can think about the Apollo mission to the moon. You had the astronauts to the moon and you had the people mission control, but there was a science backroom you didn't hear about, but the astronauts were getting information from them.
Arizona has a very good climate for these types of analog studies. You have pretty much open plains and you have a lot of geological features that are analogous to places on the moon and on Mars.
Long-term space voyages are being replicated on the ground and in orbit with the ISS. Surface habitats, power systems, food and oxygen supply manufacturing are also on the drawing board.
The human flight component would like to see an experiment where resources on the surface of Mars, from the rocks or the atmosphere, could be used to generate fuel or other parts that would enable future exploration in cutting the tie, so to speak, to Earth. So you wouldn't necessarily have to bring everything with you. You can actually manufacture it on the planet. And that's a really exciting additional component that we've been exploring and analyzing in this work.
NASA isn't the only one with its eye on this prize. ESA and now the Indian Space Research Organization have a spacecraft orbiting Mars, and they did it on their first attempt. Private enterprise is hard at work as well. Mars 500, Mars One, the Mars Society, Mars Foundation, and the Mars Initiative, to name a few. And they have volunteers lining up already for a one-way trip to Mars. It is inevitable that we will set foot on Mars in the very near future. We will stay and learn her secrets. Perhaps in the future we will be able to alter the atmospheric density through terraforming and return Mars to the world that it once was, awash with oceans and rivers, clouds and rain. Maybe some of us could call it home. Our seafaring nature has translated well to the space age, sailing out into the unknown in search of riches of one kind or another. While Europe and Asia continue their interest in the resource-rich moon, the United States and NASA have set their sights on nothing less than manned missions to Mars. Can they manage to go shore to shore on the most dangerous of unknown seas, deep space? With low Earth orbit harnessed, it's time to look further afield. To build a spacecraft and rocket system to reach Mars is a mammoth undertaking, but if successful, it will return the United States to the top of the space achievement ladder. The first requirement? A space capsule able to carry 6 astronauts for a long period of time and return them safely to Earth. Orion is its name, and it has flown once already in a shakedown. The next flight will be an unmanned test mission past the moon, followed by a third manned mission. The components for the vehicle are developed around the country, tested and checked, then passed on for assembly. The minutest bolt and circuit is designed, tested, redesigned and tested again. Slowly the systems come together with the aid of some breakthrough technology, particularly in manufacturing methods, new materials and processes. The first thing to notice is that NASA have gone back to the classic conic shape like Apollo, the safest design yet devised. Avionics, control systems, computer software, and a glass cockpit, all state-of-the-art.
And the concept was to go with a glass cockpit, and what that means is that the instruments are all images on a computer screen. They are all on the glass. So rather than flipping a physical switch, the crew brings up a computer screen and flips a virtual switch, a little icon of a switch or icon of a valve. And with the exception of 7 panels right around the computer screens, which have about 60 switches, that is all of the cockpit of Orion happens on the glass. One big benefit is a weight savings because you don't have to have a physical switch. And having a physical switch, not only is there the weight of the switch, but you also have the weight of the wire to the switch. And you have to have the weight of circuitry that takes that wire and feeds it into the vehicle computers.
Because of Orion's size, its all-important heat shield is the largest one ever made, and new processes were required to manufacture it.
The Orion heat shield has got to be able to withstand landing loads on the order of 300 to 400,000 pounds. Because we're returning potentially from the moon or beyond, and the flight duration from the time in which you commit to a return to the time you actually land, the weather conditions on Earth can be substantially different or difficult to predict. And so the Orion spacecraft has to be able to land in the ocean in a wide range of sea conditions, wave height, wave slope angle, and horizontal winds. That is what's driven us to a skin stringer architecture that utilizes a thick laminate composite skin bolted to a titanium substructure.
We bond on an ablator called the AVCoat. The ablator is the thermal protection part of the heat shield. The very outside of the ablator actually gets hot enough that it decomposes, and that's the ablation part of it as opposed to an insulator like a shuttle tile.
Then come the ancillary structures and equipment that will ride with the capsule. The escape tower, designed and tested, will pull the capsule away from the main rocket in the case of an emergency. Adapter separation from the rocket's upper stage. Parachute deployment. The connecting adapter to the EMS. The EMS is the service module attached to the Orion in flight, supplying oxygen, water, power and heating. Built by ESA, it is based on their very successful ATV program, which delivered supplies to the ISS. It will also provide the main engine thrust for deep space maneuvering.
We have, in particular, very tight schedule in front of us. So everybody's working under a high pressure to meet the dates, and this requires a very close collaboration.
I see a very motivated team, and so far as an agency we are quite happy with the performance of the European industry.
The US Navy is tasked with retrieving the capsule from the ocean. At first they train in the pool, then calm waters, then the Pacific, and finally the real thing. This is the RS-25, the Ferrari of liquid rocket engines and the main engine from the Space Shuttle program. Economically repurposed for the Space Launch System, 4 of these engines will power the main stage of the rocket. The main solid rocket boosters of the shuttle program also have a renewed life in the SLS. With another 2 segments added, the boosters will thrust for over 2 minutes.
This project has been a real fun effort in trying to take a heritage booster that had many, many years of reliability and great performance and evolve it into something bigger and better.
When we first undertook this design and qualification for the new booster, part of the mission was to make the booster more affordable and more modern. And of course, it had to be completely redesigned for a new mission. It's a larger booster, and the mission profile is sufficiently different to where pretty much everything on the inside of the booster is different. There's well over 1,000 individual processes. Working with our customer, we were able to identify several hundred areas of improvement.
We've got totally new avionics on this vehicle versus what we had on shuttle. It's state-of-the-art.
Bigger and more powerful than any previous launch system, the SLS has been under development for some time. Designing it is one thing, building it another. In new or refurbished factories and assembly shops, the body of the largest rocket ever to fly is being constructed one piece at a time. The massive hydrogen tank takes shape. The smaller oxygen tank soon follows. The interim stage for the manned flight is another hydrogen-oxygen motor supplied by cryotanks fabricated with new technologies.
So to design and manufacture this tank, we use new materials. We process the tank by automated fiber placement. The benefit of that is we can lay down the material quickly, which provides us a low-cost operation and a very lightweight tank.
We've worked on this program for 29 months, and when we started, we'd never built a tank of this size by the methods that we did. We did automated fiber placement and fluted core, just developing the robotic fiber placement equipment and way to make the skirt in one piece was a large challenge.
Each exacting piece is fabricated, test articles are run through the mill, vibration tests, vacuum tests, acoustic tests, stress tests. Nothing is left to chance. New technology and new materials for a new generation of space exploration.
So this test, there were several things that we looked at. This was the first time we used those thermal knives to start the deployment sequence, and that allowed cut some tethers that then allowed the solar array to deploy. We wanted to test the locking mechanisms to ensure that it locked properly in space, because anything that could possibly go wrong, we wanted to see test down here so that we can ensure a successful flight.
It's all about technology. If you don't develop technologies for the future, you won't go where you want to go. So composites will decrease the weight of the tanks. It'll increase the payload performance of the launch vehicle. It'll give us, it basically enables things that we don't have today.
Soon the mighty rocket will lift human beings up further than ever before. The flight to Mars will be a long one, too long for a crew to sit in a capsule. Habitat and supplies will also be lifted to orbit and assembled. Several companies have been selected by NASA to carry out studies for a suitable system to do the job. A bit of competition is always good for invention. Bigelow Aerospace, with its Expandable Activity Module, or BEAM, currently being tested on the ISS, will develop and test a prototype of X-Base, a 330 cubic meter expandable habitat. Boeing of Houston is developing a modular habitat system that leverages more than 15 years' experience in designing, developing, assembling on orbit, and safely operating the International Space Station. Lockheed Martin will refurbish a multi-purpose logistics module into a full-scale habitat prototype that will include integrated avionics and ECLSS. Orbital ATK will mature the mission architecture and design of their initial cislunar habitat concept based on the Cygnus spacecraft that now supplies the ISS. Sierra Nevada Corporation's space systems will study and refine a flexible architecture and concept of operations for a deep space habitat that draws on the lessons of 3 to 4 commercial launches to construct a modular, long-duration habitat. NanoRacks, in conjunction with its partners, Space Systems Loral and the United Launch Alliance, referred to collectively as the Ixion team, will conduct a comprehensive feasibility study regarding the conversion of an existing launch vehicle's upper stage, or propellant segment, into a pressurized habitable volume in space.
So if you're designing spacecraft to be in the Mars orbit, then the studies we're doing on Space Station can be applied and help us design more durable spacecraft for that Martian atmosphere. MISSE stands for the Materials International Space Station Experiment. We do study the durability of polymers in terms of their mechanical properties with radiation exposure. And we hear a lot about the radiation exposure impact on humans for flights to, say, Mars. But polymers and other materials that are used on spacecraft can also degrade from radiation, and that's one of the things I study. The MISSE 8 experiments do take a little bit of time because we do very careful dehydration measurements of the samples after they've been in space. What we found is that the Teflon erosion rate is highly dependent on the amount of sunlight and possibly the heating too. You need to know which of these environments it's going to be exposed to because it'll erode at a different rate depending on the environment.
Assembling spacecraft in orbit and fueling them for the long journey to Mars sounds simple enough. On-orbit refueling is anything but simple. NASA have been developing a system for unmanned refueling for quite some time and have a test article on board the ISS.
We can take a pick-and-place robot, put the tool wherever we need it to be, and all it needs to do is drive that tool because the smarts are in the tool. So that's what we learned from working on Hubble, is you put a smart tool with the astronauts and accomplish, both things. You've got smart tools and astronauts working together. Now we're putting smart tools with robots and trying to accomplish the same type of things we did on Hubble.
Aimed at developing capabilities for servicing, even refueling spacecraft on orbit, RRM is like doing precise surgery at a distance, doctor and patient separated by the void and vacuum of space. It's tough, but the payoff is huge.
Robotics can do things that humans can't do in terms of precision, in terms of control, holding a particular spot for 6 hours while engineers on the ground debate what to do. We can't ask a human to do that.
The robot is a very stiff, rigid interface. It's not forgiving like an astronaut's hand. So we have to take that into account. When you push on something really hard with the robot, you build up really large contact forces. When the astronaut pushes on something, his wrist might give. He's got his own internal sort of software compliance running. But in order to accommodate the robot so we don't break anything, we have to build features into the tool, features into the software, just getting the robot to go where you want it to go. And, they don't position precisely. So you have to do things like build lead-in into the tool. An astronaut could probably just get it right on there because he's right there. So we do have to do things to make them, very specific to robotic operation.
That task successful? Next stop, Mars. The first manned mission to Mars will probably only orbit the planet, checking out all the gear and processes, even launching communication satellites, and finalizing landing sites in preparation for the next mission, which will then make the descent to the surface. And that has a whole new set of problems to overcome. Unlike the Moon, Mars has stronger gravity, about 0.6 of Earth's, but it does have an atmosphere where parachutes can be used, although the atmosphere is very thin and not very deep.
Well, it's a funny thing about Mars, but if you take the average of the planet, the average height of everything in the planet, it turns out that most of the north is 2 kilometers below that, and most of the south is 2 kilometers above that. And it's just, we always land in the north because there's a lot more atmosphere. If we land in the south, it's like 4 kilometers less of air to come to a stop. In fact, at the altitude of the mountains in the south, the Mars Science Laboratory was still supersonic as it was descending into the crater that it was reaching in the north.
Assuming the need to pre-position habitats, supplies and equipment on the surface prior to a human landing, NASA and its partners are looking at several solutions. One is the HIAD, or Hypersonic Inflatable Aerodynamic Decelerator. This is basically a very large inflatable heat shield, much larger in area than the payload, able to slow the craft considerably faster than a standard spacecraft heat shield. Plans are to test the system on a payload from the ISS, utilizing a Cygnus resupply spacecraft. Once lower in the atmosphere, parachutes will further slow the payload to an altitude low enough for rocket engines to take over. Morpheus and the Zombie flight systems have matured over the last few years and are capable of delivering cargo to a planet's surface autonomously, avoiding rough terrain or other obstacles without human intervention. adding yet another building block to our human effort to explore the solar system. From the beginnings of our solar system 4.5 billion years ago, there remain tantalizing clues to its evolution. Remnant debris, asteroids, and comets. They vary in size from grains of dust to mountainsides, from footballs to planetoids. They were the building blocks of the planets and perhaps carry the origins of life itself. Now within our grasp, these rocks of ice and dust are ready to give up their secrets. Asteroids are believed to be made of chondrules, flash-heated grains of rock within the stellar disk of our forming solar system. These chondrules clustered together, forming the first asteroids and the building blocks of the planets. Once the solar system had evolved, there was a lot of asteroid material left over. They cover a broad spectrum of types. The largest of these are minor planets or planetoids, large enough to have an ovoid shape. This category took the previous planet Pluto off the major list and onto the minor. The smallest remnants of debris are often called meteoroids. There are in fact several minor planets. Some have been seconded into planetary orbit and become moons. The traditional asteroid belt between Mars and Jupiter has one called Ceres, the largest and the first to be detected. Our first close-up of an asteroid was courtesy of Galileo on its flight through the main asteroid belt towards Jupiter. It photographed 951 Gaspra, an S-type asteroid with an average diameter of just over 6 kilometers. The S stands for stony composition. Galileo then photographed the larger 243 Ida at 15.5 kilometers wide, revealing that it has its own moon named Dactyl. Asteroids are not limited to the asteroid belt between the orbits of Mars and Jupiter. Many orbit much closer to Earth and are known as near-Earth objects, or NEOs.
Radar is a very powerful instrument that we use to study near-Earth asteroids. Asteroid Toutatis was millions of kilometers away, and we were able to resolve surface rocks. We could see boulders.
There are currently only 2 radar facilities in the world that have sufficient sensitivity for doing regular observations of near-Earth objects: Arecibo and Goldstone.
Even the most powerful optical telescopes, and I'm talking even, Hubble telescope, they can only see this asteroid as a point of light. It is just too far and too small.
It provides an extraordinary opportunity to get very detailed radar images.
You are transmitting microwaves. It's propagating at the speed of light toward the asteroid. It is bouncing back. And this radar echo is containing surface features of the asteroid. It's telling us about its rotation, and it's very precisely pinpointing its distance from the radar.
These asteroids were imaged with ground-based radar. BL-86 revealed it has its own moon, and asteroid HQ-124 passed very close to Earth, some 3.25 times the distance to the moon. It is due to return sometime in the 24th century. Scientists are looking much more closely at these objects for their potential to pass through Earth's orbital plane and perhaps pose a threat. The most common type of asteroid is the C-type carbonaceous, accounting for about 75% of known asteroids. The probe near Shoemaker was the first dedicated asteroid probe launched by NASA. It photographed 253 Mathilde, a C-type, then moved on to 433 Eros, the largest visited at the time, where it orbited, took extensive measurements and, more by accident than good planning, landed on the asteroid, the first probe to do so. Deep Space One, an experimental NASA probe, was sent to investigate an asteroid 9969 Braille. Technical errors returned poor imagery. However, the probe continued on to its second rendezvous, for the first time with a comet, 19P Borrelli. Comets are closely related to asteroids, but originate from the cold, dark outer boundaries of our solar system.
Comets are bodies in our solar system that have been left over ever since the solar system formed, some 4.5 billion years ago. And therefore, when we look into comets, we look into the past of our solar system. And so by investigating the details of comets, how they formed, how they evolved, we can actually have a glimpse into how our solar system formed, and in the end, how the Earth formed and why we are here.
Comets have been recorded throughout history, as they are easily observed when close to the Sun, often considered an omen. One comet of note was Halley's. In 1986, Halley's comet returned once again, and this time it was met with a veritable armada of space probes. The first attempt at a space rendezvous was with the International Comet Explorer, or ICE. It passed through the tail of comet 21P Giacobini-Zinner on its way to meet Halley. The European Space Agency sent Giotto. The Russian and French sent two probes via Venus, Vega 1 and Vega 2. Japan sent Suisei and Sakikage, that country's first deep space probes. Their measurements went on to refine the targeting for Giotto to make a much closer pass of the comet's nucleus than first planned. In 1994, astronomers and scientists were given an unexpected treat. Comet Shoemaker-Levy broke apart and struck Jupiter in a spectacularly violent fashion. Comets required more study. The Stardust probe was dispatched to investigate 5535 Anne Frank, Wild 2, and then the Tempel 1 comet. It returned a sample of cometary tail to Earth.
Our biggest discovery that we did was looking at this cometary material that was returned from NASA's Stardust mission. And the Stardust mission went up, rendezvoused with a comet, brought back very small amounts of material, comet material and comet exposed material. We had basically one shot at looking at this, and it was really pushing our limits of detection. So I spent about 2 years optimizing our technique, really rehearsing, practicing, getting everything as perfect as possible before the one day of doing measurements. It's sort of all leading up to one big game, one big day. And also just working with meteorites and working with the cometary material, I'm working with something that's 4.5 billion years old that very few people ever get to play with, and the few days of being able to do the actual measurements make up for all of the rehearsals that it takes.
JAXA launched Hayabusa to study asteroid 25143 Itokawa and to retrieve a sample from the surface in a touch-and-go maneuver. The mission took a total of 7 years to accomplish, with the sample return pod retrieved from the Australian outback in 2010. Launched a year earlier by the European Space Agency was a very ambitious spacecraft called Rosetta. Its goal? To land a probe on a comet, 67P Churyumov-Gerasimenko. Just getting there was to prove a challenge in astronavigation.
But when you want to rendezvous with a comet, you have to accelerate the spacecraft and
match the same velocity that the comet has around the sun. So this is the problem, not only the distance, but also the velocity. There is no rocket that can give us the velocity needed to be as fast as the comet. Like close to a planet, and you use the gravitational attraction of the planet to actually accelerate your spacecraft.
It passed by asteroids 2867 Steins and 21 Lutetia.
Lutetia is a very strange target, a very strange asteroid. We believe that it may be a C-class asteroid, which means that it is very primitive. However, it shows from ground-based and also spaceborne observations that Lutetia does not look completely like a C-type asteroid, and we are really puzzled about what it really may be.
The spacecraft then moved on to its primary target, Comet 67P.
The nucleus is pulling the spacecraft out of its planned orbit, and that can be seen as a shift in frequency of the transmitted radio signal from the spacecraft. And the extent of this frequency shift is a measure of the mass of the comet nucleus, so we are able to weigh the nucleus here.
There is no ice at the top, so it's covered by a mantle that we consider is essentially made of organic material. That's why it's very dark. And this material is one of the key things we would like to explore and analyze.
These organics may hold the secret to life on Earth.
What it's all about is the carbon chemistry. How much did the comets bring to Earth? So was it just the right elements, the right building blocks, or was there more information in it when these comets already arrived?
To try and answer these questions, ESA attempted one of the most daring missions mankind has ever undertaken, to land a probe on the surface of the comet. Landing on a comet is one of the hardest things that has ever been done by the human species.
This is the comet. It's roughly a 1 in 1,000 model, so the real thing is 1,000 times bigger. The landing site is roughly here, which we're aiming for to deliver the lander. It's the flattest part we could find. What we are studying at the comet with the instruments are basically what are the ingredients, which materials are present, and coming back to one of the objectives of the mission, how complex are the materials present at the comet.
Landing means flying very, very slowly over the comet and then gently pushing away the lander. It's not a landing like you can imagine on the moon, where you come with rockets and you have to brake. Here the problem is the opposite. You have to really touch gently the comet. The forces involved are very small.
If I get meaningful data, that would be just marvelous. If the descent works, the landing is okay, we receive a sample, and the whole thing runs smoothly, that would be just great. But we need a lot of luck, really. And we had a lot of luck already.
So we are sitting on the surface. Philae is talking to us, more data to come and to be analyzed right now. Going down, which it should do, of course. We are there, it's done its job. We are on the comet.
The science has started now. We have the first results that give us the first comprehension of what we think the comet is, where it started from. Now, for the rest of the year, we'll watch how the comet evolves. We'll unlock how the comet works. We're looking at where the gas and the dust start to accelerate from the surface and how that beginning of the coma, that birth of the coma works. So how the coma develops as it does to higher altitudes. This region has only ever been theoretically constrained or modelled. These will be the first measurements we make in this area or this region, and that's a really big, important target for us.
Eventually, the tiny probe shut down.
Having Philae reactivated is not so likely, but it's not impossible. Philae was designed to hibernate, was designed to switch off and be able to reactivate itself. Of course, we expected this to be a duration of a few days or a few weeks, not a few months. But okay, we will see. Maybe we are lucky, and the units have survived these months, and we reactivate in June, July.
While observing the asteroids, scientists were surprised to find one with what looked like a cometary tail. After careful study, scientists realized they were observing the results of the impact of two asteroids. 596 Sheila had been struck at high speed by a small asteroid. The impact hit with the force of a 100-kiloton nuclear bomb. NASA had done something similar with Deep Impact, a probe sent to Comet Tempel 1, where it dispatched a kinetic impactor which struck the comet to study the impact and the debris thrown up as a consequence. Soon after, NASA launched another small ion-powered probe, Dawn, which also had an extraordinary mission: to travel deep into the asteroid belt between Mars and Jupiter. Its targets, two of the largest asteroids in the solar system. Dawn rendezvoused with 4 Vesta and orbited it for over a year, returning a wealth of data. Dawn then departed and cruised towards Ceres, the largest of the asteroids, a planetoid, where it has obtained orbit and begun its study. JAXA, the Japanese space agency, has recently launched a second Hayabusa probe, this one with many improvements over the first. Its target is the C-type asteroid 1999 JU3. It's expected to reach its destination in 3 years, collect samples, and return to Earth by 2020. NASA has announced the OSIRIS-REx sample return mission to asteroid 1999 RQ-36, better known as Bennu. It's expected to launch sometime in the near future, and after a 2-year journey, orbit and map the surface before touching down to retrieve 2 kilograms of material. The probe sample's return is expected in 2023. there is also a practical reason to study asteroids. In 2013, an asteroid with a mass of about 9,100 tons exploded over Chelyabinsk, Russia, with the force of 20 Hiroshima bombs, causing 1,500 injuries and damaging 7,000 buildings. It isn't the first asteroid strike on Earth, as the dinosaurs can attest to, and probably not the last. Through the United Nations, ESA and other major space agencies have established a safeguard program.
The NEOWISE data have returned two very important findings. First, we've been able to determine that we've found 93% of all the near-Earth asteroids that are out there that are larger than 1 kilometer. We've also been able to tell that there are somewhat fewer near-Earth asteroids that are larger than 100 meters than were previously thought. However, fewer does not mean none. That leaves about 15,000 asteroids larger than 100 meters that remain to be found.
This advisory group is also planning intervention missions if needed.
We think that we can cope with deflecting an asteroid with two different technologies mainly. One is what we call kinetic impactor, hitting the asteroid and pushing it out of the way. The second one is take a heavy spacecraft and use it as, say, a gravity tractor. So by the mass of the spacecraft, you pull the asteroid away.
There is one project in the planning stage to snag a small asteroid in the near-Earth region and drag it into a lunar orbit. There it can be met by astronauts aboard an Orion capsule who will study the asteroid firsthand, take extensive samples, and return to Earth. For the more we know, the better prepared we are to protect our place in the solar system. As the latest successes and failures come and go, Mars continues to give up her secrets. Invisible clouds are revealed with ultraviolet light, and the search for the source of methane continues with ExoMars. As we prepare to land humans on the Red Planet, getting there is one thing. Staying long-term is another. Can we really conquer this planet? The joint European and Russian ExoMars made a successful launch with great applause and journeyed uneventfully to Mars.
Our instrument is devoted to the measurement of trace gases by measuring the solar radiation passing through the atmosphere of the red planet.
Some scientists are trying to determine the local origins of methane gas. Is it a sign of life?
We're interested in looking at where the trace gases may be coming from. So, for example, if methane is there in abundance and you see it locally coming from a particular place, you'd like to know whether it's got a volcanic origin, whether it might be old gases that have been trapped in ice that's then released due to sublimation processes, things like that. It doesn't have to be biology. And it's important to recognize here that I'm a little bit of a skeptic. You know, I don't go for this life business. I try to keep the other guys honest.
ExoMars made a perfect orbit insertion around Mars and commenced flexing its considerable technological muscle. Returning high-resolution images and stereoscopic observations, enabling highly detailed three-dimensional maps to be created. However, the mission didn't go entirely to plan. The lander half of the probe, the Schiaparelli lander, made an ideal separation from the orbiter and commenced a textbook descent. The heat shield functioned as expected, all systems go. The drogue chute, then the main, were deployed correctly. Then the curse of Mars struck. 1 second's worth of erroneous data was passed on to the onboard guidance and navigation control system. When this odd data was merged into the computer's algorithm, it generated a false altitude reading, placing the lander below ground level. This triggered the premature release of the parachute and back shell. Braking thrusters fired and the lander's on-ground systems began operating, thinking it had landed. Unfortunately, it was still 3.7 kilometers in the air, and the universal laws of gravity took over, the lander smashing helplessly into the ground. Satellites overhead soon located the parachute and back shell, and then the lander itself, looking like a squashed bug on a windscreen. The lander was, however, a technology demonstrator, and the problems that arose could be quickly remedied. So ESA is still fully confident of the technology and will proceed with the next lander containing the ExoMars 2020 rover. With the latest analytical technology, the rover will drill down as far as 2 meters into the Martian soil, looking for those elusive microbes. This is the Interact Centaur rover from ESA. It can be remotely controlled from orbit by ESA astronauts. NASA has its own version. They are one of the tools for future investigations on Mars. The proof of concept in Earth orbit will make it a reliable tool on Mars. Astronauts can maneuver the robot to a test table, then perform very fine operations with a number of tools and devices. It could even help assemble hardware and habitats on the Martian surface while astronauts orbit overhead. NASA's Curiosity rover continues its epic journey across Gale Crater, covering over 14 kilometers in its 3 years of operation. It will soon be replaced by its smarter big brother, Mars 2020 rover. Built on the same configuration, the 2020 rover looks strikingly similar to Curiosity, with some improvements. A landing hazard redirect feature to avoid any rocky landings, new wheels and treads for better climbing, audio microphones to hear what's going on, and a rock core sampling drill. One of the main goals of the Mars 2020 mission will be to determine the potential habitability of the planet for human visitors. Scientific instruments on board include an advanced stereoscopic imager, environmental sensors for temperature, wind speed and direction, pressure, humidity and dust particle size and shape. PIXL is an X-ray fluorescence spectrometer for chemical analysis of Martian soil. RIMFAX, a ground-penetrating radar to study subsurface geology, and SHERLOC, an ultraviolet laser spectrometer for the study of fine-scale mineralogy and organic compounds. The final instrument package is MOXIE, a technology demonstrator designed to generate oxygen from the carbon dioxide in the Martian atmosphere, a critical piece of kit if humans are going to survive on Mars. It will generate oxygen for fuel and breathing. Mars's atmosphere is predominantly carbon dioxide, plus trace amounts of argon, nitrogen, oxygen and carbon monoxide. Its mean pressure is 600 Pascal. That's about 0.6% of Earth's air pressure at sea level. So another vital piece of equipment is the spacesuit.
In the future, I'm looking forward to spacesuits that are much more of a tool for the astronaut, that is more integrated with the human, and is less of an encumbrance and more of a help.
Several spacesuit designs are underway. There are many specific requirements. The flexibility to walk and move on a low-gravity planet, for example, and the ability to bend down and pick things up. They must also be able to illuminate the way forward. Ease of access for donning the suit is important, as are clearly a pressure garment and thermal insulator for the low pressure and temperatures on Mars. The latest prototypes, like the Z2 and the PXS, are going through extensive development for surface use. The Z2 meets the walking and flexibility requirements. PXS is a more traditional style of suit, but also quite flexible.
My my main responsibilities on this spacesuit is the suit control assembly, and that's the box that sits right here on the front of the suit. And it allows the crew member to control their life support components, such as their cooling and their pressure, and it also controls a lot of the electronics, such as the radio and the volume, and they can see some of the data that's coming back and forth from the suit computer to that display. So one of the great things about this job is that after designing the box, I'm able to get into the suit, since it's one of the smaller sizes, and we can actually see what the limitations are, with my own hands and eyes, and not just hear that secondhand from another test subject that would be looking at the same data. And then to take that back and then to go build the next prototype and incorporate the changes that need to be made so that it works better the next time.
Another critical element for surviving on the Martian surface is power. The sunlight reaching Mars is just a little more than half of what we receive on Earth. In addition, there are regular dust storms, and solar power may not be sufficient of itself. It will have a role to play, but other sources of electric power may be required. NASA has been developing fission power plants for such requirements, working on 2 systems. The less powerful technology demonstrator unit for spacecraft and surface operations requires watts of power numbered in the tens or 100s. Kilopower addresses the need for surface power from 1 to 10 kilowatts for human habitats and scientific exploration in the harsh environments of Mars and beyond. The journey to Mars is a long one, not in kilometers as such, but where the scientific, technical, and engineering hurdles that need to be overcome are concerned.
What are the things they need to know to be able to safely land, live, and return from Mars? The scientific knowledge, the technologies that we need that can make human exploration of Mars happen are within our grasp. In our lifetime, we actually can see humans land and work on Mars. A major step in this direction of planning has been the definition of what we call human exploration zones. This is a region we will land, we will live, we will use resources in many different ways, and we want to go to a variety of scientifically exciting locations. Do it in ways that humans, and only humans, can do.
One drawback: humans are fragile. To function correctly, they have a specific set of requirements: atmospheric pressure, air to breathe, water and food for nourishment, rest and sleep, and protection from radiation. Mars offers very few, but it does have an abundance of radiation. Mars habitats have been the subject of years of engineering and technical research. NASA has even thrown open the doors to students and architects to help design and develop suitable accommodation. There are minimum requirements around the number of occupants and length of stay. With limits on payload weight and mass, using local resources like sand, rock, and ice to develop habitats has been strongly recommended. The 3D print competition threw up some very good ideas and designs, some of which NASA is developing further. The three finalists were Team Lava Hive, Team Gamma, and Team Space Exploration Architecture and Clouds Architecture Office of New York. Their ice house included all the components required to assemble the habitat in situ on Mars. The vehicle lands at the designated site and deploys several robots and water storage assets. The robots set about building a secure base, utilizing local sand sintered together with lasers. An inflatable plastic membrane is then deployed along with internal airlocks. The robots source local water, which is used to 3D print the inner lining of the membrane. Water is an excellent shield for radiation, and being translucent, it allows sunlight in. Hanging gardens and windows add a touch of home. NASA Langley has developed the Ice Dome concept from this prize-winning concept. Creating a colony on another planet really is a mammoth task. Leaving aside the training, technology and traveling, not to mention the money, building a functional, self-sustaining village will need people from all walks of life. Apart from the scientists, geologists and prospectors there to do the primary job, people will not cope with living in prefabricated temporary shelters. A town will have to be built from local resources. Engineers, builders, fabricators, electricians, plumbers and mechanics will all be in great demand. So will IT and communications experts, doctors, nurses, pilots, farmers, botanists, and the list goes on. On the other hand, not everyone gets the chance to colonize an entirely new planet, so that is one draw card. If Mars 1 is any example, it seems there will be plenty of volunteers for this dangerous work. One question hasn't been asked yet, and it's of fundamental importance. Can humans live long-term in space or on another planet with reduced gravity, less sunlight, and lower atmospheric protection? One proposal before NASA at the moment is the multi-generational independent colony for extraterrestrial habitation, autonomy and behavior, which contracts nicely to MiceHab, and it's exactly what that name suggests. MiceHab is a spacecraft and autonomous support system to study the long-term generational health of mice in Martian gravity. The vehicle would be placed in a stable orbit close enough to the Moon to be within easy reach by manned missions. The MiceHab would be deployed and spun up to Mars-like gravity. It would then support the growth of a large mouse colony for a year or longer, studying reproduction and maturation of lab mice through multiple generations, which is to say, much faster than human subjects. The vehicle would house multiple levels of mouse enclosures designed to be serviced and cleaned by an onboard robot. The system would take care of feeding, watering, and cleaning the mice, including their medical care. Breeding would be selectively controlled over generations in the low gravity. The mice would also be studied for any physical, behavioral, or metabolic changes. The project would also collect data on deep space radiation and the hazards posed to humans. The robotic systems would also provide an in-situ demonstration of autonomous activities like maintenance for long-duration deep space missions. From time to time, astronauts would dock with the habitat to collect data and specimens. MiceHab will allow humans to prepare to live independently from Earth in space and on the surface of Mars, and help answer that critical question we started with. Could humans survive long-term in low-gravity environments?